Imagine driving a car at night with the headlights off and the dashboard dark. You have no idea how fast you are going, whether you have enough fuel, or if the engine is about to fail until it smokes right in front of you. That is exactly what deploying cloud infrastructure without monitoring feels like. Azure Monitor acts as your cockpit, giving you the visibility you need to keep your systems running smoothly. Without it, a single unmonitored virtual machine can silently consume all your compute quota and trigger unexpected billing spikes that drain your monthly budget before you notice the slowdown. In this lesson, we will cover the core pillars of Azure Monitor. We start by distinguishing between the two main data types you will encounter on the exam. Then we walk through the practical steps of setting up a log analytics workspace and collecting data using the Azure CLI. After that, we look at alerting strategies to turn raw telemetry into actionable responses. Finally, we review best practices to ensure your monitoring remains cost-effective and reliable under heavy production load. Azure Monitor operates on a telemetry model that categorizes data into two primary streams: metrics and logs. Metrics are numerical values collected at regular intervals, perfect for graphing trends and triggering real-time alerts based on thresholds like exceeding 90% CPU utilization. Logs contain unstructured text records like error messages and stack traces, which are essential for deep-dive troubleshooting when a metric indicates a problem. Confusing these two streams will cause you to fail performance queries or miss critical security events in your audit trails. Let's define metrics precisely. Metrics are lightweight numerical values that describe a system at a specific point in time. They are stored for long periods and are ideal for near real-time alerting. For example, CPU percentage or request counts are metrics. When you see a spike in the graph, you know exactly what is happening numerically. If you attempt to run complex text searches on metric tables, your queries will time out and waste precious compute credits during critical production incidents. Here is a practical KQL query to visualize metrics. We start with the Insights Metrics table, which stores performance data. We filter for the last hour using time-generated and add a where clause for computer equals prod server 01. Then we narrow down to CPU usage by checking the name field equals CPU usage percentage. Finally, we summarize the average value per computer and render it as a bar chart for easy reading. Skipping this filtering step will cause your query to scan millions of rows and trigger unexpected workspace costs. Now let's look at the procedure for setting up data collection. This is a multi-step process that ensures your environment is fully observable across every subscription tier. We will walk through each step with the specific commands you need to run in PowerShell or the Azure CLI. Skipping any configuration phase will leave critical performance counters uncollected and prevent you from diagnosing latency issues during peak traffic windows. For the first step, we create the Log Analytics workspace. This command uses the Azure CLI to provision the workspace in your subscription and resource group. You specify a unique name and the pay-as-you-go pricing tier to start collecting data immediately. Running as Monitor Log Analytics workspace, create with the correct location parameter, ensures your data stays compliant with regional residency requirements while avoiding cross-region egress fees during peak monitoring hours. With the workspace created, we move to the second step. You must install the Azure Monitor agent on your virtual machines. This agent collects guest-level data like performance counters and event logs that platform metrics cannot see. Without this extension running continuously, you will miss critical application crashes inside the operating system and fail to meet compliance auditing standards for internal security reviews. To install the agent, we use the VM extension command. This links your virtual machine to the Log Analytics workspace you just created. The command specifies the publisher, version, and the workspace ID to ensure the data flows correctly from the guest OS. You must verify the extension status returns succeeded within 2 minutes. Otherwise, telemetry will drop silently and break your end-to-end tracing pipelines. Finally, we configure the data collection rule. This rule defines exactly what data to collect and where to send it. By using DCRs, you can filter logs at the source to control costs and focus on the most diagnostic information. You must explicitly map each rule to a specific resource group. Otherwise, default ingestion rates will spike unexpectedly and overwhelm your monthly allocation limits. Here is a snippet of a data collection rule JSON. This rule targets the Windows event log and syslog facilities. It routes the collected data to your log analytics workspace. This granular control ensures you only pay for the logs that provide value. You must validate the JSON schema against the Microsoft as monitor specification before deployment. Otherwise, malformed routing tables will discard critical security events and leave blind spots in your audit trail. Azure offers several tools for monitoring, and choosing the right one depends on your goal. Azure Monitor provides full-stack logs and metrics. Azure Advisor focuses on best practices and cost optimization. Service Health tracks the status of the Azure Cloud platform itself. Network Watcher handles connectivity and packet captures. Mixing these services up during an exam will lead you to select the wrong diagnostic tool for a specific performance bottleneck or outage scenario. Alerting turns data into action. You should focus on symptoms that impact the user experience, such as high latency or failed requests, rather than just component busyness. Use severity levels to prioritize alerts and automate remediation where possible. This prevents alert fatigue and ensures your team responds to critical issues immediately. Configuring more than 5 active rule groups per workspace will overwhelm your notification channels and cause engineers to ignore legitimate warning thresholds. Remember this principle. We monitor not to create pretty charts, but to provide a stable experience for our customers. If your monitoring does not help you find a problem faster or prevent an outage, it is just noise. Constantly refine your alerts based on actual incidents. You should schedule quarterly reviews of every active rule group to disable redundant thresholds and redirect saved licensing fees toward higher priority diagnostic workspaces. Let's check your understanding. Which data type would you use to find the specific error message and stack trace when a web application crashes? Is it metrics or logs? You must select logs because they store unstructured text records and detailed exception outputs. Choosing metrics instead will only show you aggregated failure counts, leaving you completely blind to the root cause code lines that require immediate patching. Here is how the data flows through Azure Monitor. Data originates from sources like VMs or applications. It is collected by agents or SDKs and sent to a log analytics workspace. From there, you can query it with KQL, visualize it in dashboards, or trigger alerts based on defined rules. You must verify the ingestion endpoint returns HTTP status code 200 before assuming telemetry reached the backend. Otherwise, silent transmission failures will corrupt your historical trend analysis. We have covered the essentials of Azure Monitor. You now understand the difference between metrics and logs, which are your 2 primary data streams. You know how to set up a workspace and install the agent to collect data. We discussed alerting strategies to focus on user impact, and we reviewed best practices for cost management and observability. Mastering these configurations will directly improve your exam score by helping you quickly eliminate incorrect diagnostic options under timed conditions. For the AZ-305 exam, focus on distinguishing when to use metrics versus logs. You will likely be asked to choose the right tool for a scenario, So know that Advisor is for best practices and Service Health is for platform status. Remember that log analytics uses KQL, and always consider cost management by filtering data at the source. Practicing these distinctions with real CLI commands will build the muscle memory you need to confidently select the optimal monitoring architecture under strict time limits. Imagine you are driving a car at night with the headlights off. You have no idea how fast you are going or if an obstacle is approaching until it is too late. Running cloud applications without telemetry feels exactly like that. Azure Monitor solves this blindness by providing a unified platform to collect, analyze, and act on data from your entire environment. We will master the architecture and configure its diverse data sources effectively. Skipping these steps causes silent failures, so we will cover every component carefully for your exams. We start by distinguishing metrics and logs in Azure Monitor. Next, we explore the Log Analytics workspace as your central hub. We then configure platform sources using diagnostic settings and the CLI. After that, we deploy the Azure Monitor agent for guest OS monitoring and instrument applications with application insights. Finally, we review exam tips to apply these concepts under test conditions. Misconfiguring CLI flags breaks pipelines, so we will walk through each step methodically to guarantee full observability before the exam. Azure Monitor organizes all telemetry into two distinct categories: metrics and logs. Metrics are lightweight numerical values captured at specific points in time, making them perfect for near real-time alerting and dashboards. Logs are detailed event records that provide rich context for deep analysis and root cause identification. Understanding this distinction is critical because each type requires a different storage backend and query language to analyze effectively. Confusing these backends causes query failures during the exam, so we will emphasize their retention periods and CLI routing requirements throughout this module. Let's compare these two data types side by side to solidify the differences. Metrics consist strictly of numbers and are stored in a time series database optimized for fast numerical aggregation. Logs contain text or structured records and live inside a log analytics workspace, which powers complex KQL queries. You will use metrics primarily for building performance dashboards and triggering immediate alerts, whereas logs are your go-to resource for auditing events and tracing complex application failures across multiple systems. Mixing these storage targets during labs triggers validation errors, so we will highlight the exact threshold values and log retention defaults you must memorize. The Log Analytics workspace serves as the central hub for most of your operational insights. It is more than just a storage bucket. It is a powerful analytics engine built on Azure Data Explorer. This workspace allows you to collect, index, and query massive volumes of log data from various sources simultaneously. When designing your monitoring solution, routing logs to a single workspace enables cross-resource correlation and simplifies your querying strategy significantly. Failing to assign proper RBAC roles blocks diagnostic queries, so we will emphasize the exact permission sets required for exam scenarios. Azure provides 3 primary platform sources to monitor your infrastructure automatically. First, the activity log records subscription-level management events like resource creation or updates, providing a historical record of who did what and when. Second, Azure Platform Metrics deliver numerical performance data for most resources without any configuration required. Finally, resource logs capture detailed operational insights specific to each resource type, but you must explicitly configure them using diagnostic settings to forward the data to your preferred destinations. Overlooking the 90-day retention limit causes compliance gaps, so we will detail the exact CLI parameters needed to extend and secure this historical data stream. Visualizing the data flow helps you understand how telemetry moves through your environment. Telemetry originates from your Azure resources, applications, or guest operating systems. This data flows into the Azure Monitor ingestion pipeline, which routes it based on type and configuration. Logs typically land in a log analytics workspace for querying, while metrics enter the time series database. You can also route heavy log streams to Azure Storage for archiving or event hubs for external SIEM integration using diagnostic settings. Bypassing ingestion endpoint validation causes dropped packets, so we will walk through the exact network rules and private link configurations required for secure data transmission. Let's walk through configuring diagnostic settings using the Azure CLI to send app service logs to a workspace. First, we capture the resource ID of your web app into a variable. Next, we retrieve the resource ID of your target log analytics workspace. Then, we run the diagnostic settings create command, passing the app ID and workspace ID. We specify the log categories to enable inside the JSON payload, ensuring HTTP logs are captured. Finally, executing this command instantly routes the traffic logs to your centralized workspace for analysis. Skipping the required flag prevents data ingestion, so we will verify each parameter against the official Azure CLI reference documentation before deployment. For virtual machines and hybrid servers, you must deploy the Azure Monitor agent to collect guest OS data. This unified agent replaces older extensions and operates using data collection rules to specify exactly what data to gather. It captures performance counters like CPU usage, Windows event logs, Linux syslog, and custom text files. The agent then routes this collected data efficiently to your log analytics workspace for logs or the Azure Monitor metrics database for performance tracking. Forgetting to assign the monitoring contributor role blocks telemetry collection, so we will emphasize the exact IAM assignments needed to secure agent communication endpoints. Once the agent is deployed, you can query performance data directly in your workspace using KQL. The query starts with the perf table to access performance counter records. We filter specifically for the processor object and the percentage of processor time counter. Next, we summarize the average value grouped by computer name and bin the timestamps into 5-minute intervals. Finally, we render the result as a time chart to visualize CPU utilization trends over time. Neglecting to specify the exact counter name causes null results, so we will validate each KQL syntax rule against the official documentation before running production workloads. Let's pause to check your understanding of the core architecture. The question asks which component handles detailed error messages and audit trails effectively. You should choose the Log Analytics workspace because it stores logs as text records optimized for searching and correlation. Metrics are numerical and lack the textual context needed for auditing, making the workspace the definitive choice for deep analysis and root cause identification. Selecting metrics instead of logs fails validation, so we will reinforce the exact table names and retention policies you must distinguish during the certification exam. Beyond platform resources, you must monitor your actual applications and custom data sources. Application Insights provides deep IPM capabilities by tracking requests, dependencies, exceptions, and user sessions automatically when you instrument your code with SDKs. For custom telemetry that does not fit standard categories, you can ingest text files via the HTTP Data Collector, IPI, or the Azure Monitor agent. Custom numerical metrics can be pushed directly to the time series database using REST APIs for complete observability. Misconfiguring the ingestion endpoint URL breaks data flow, so we will emphasize the exact authentication headers and sampling rates required for reliable application monitoring. Let's examine how to query application telemetry once it reaches the workspace. The query begins with the requests table to access HTTP traffic records. We filter the dataset to show only responses with a 50 status code, isolating server errors. Next, we project the specific columns we need for troubleshooting, including the timestamp, operation name, URL path, and client IP address. Finally, we order the results by time in descending order to see the most recent failures first. Forgetting to filter by app ID returns cross-resource noise, so we will validate each KQL operator against the official schema before deploying monitoring queries. Here is the most important principle to remember as you design your monitoring solution. Centralizing all log data into a single log analytics workspace enables powerful cross-resource correlation and dramatically simplifies your overall architecture. When every resource routes its logs to one hub, you can join tables across different services to trace complex workflows and troubleshoot issues that span multiple components efficiently. Fragmenting workspaces increases query latency and licensing costs, so we will emphasize the exact workspace, sizing guidelines, and data retention thresholds you must calculate for certification scenarios. We have covered the essential architecture and data sources for Azure Monitor. You now understand that metrics provide numerical time series data, while logs offer detailed text records stored in a log analytics workspace. Remember to configure diagnostic settings on every Azure resource to capture operational logs, deploy the Azure Monitor agent for guest OS visibility, and instrument your applications with Application Insights SDKs. These steps ensure complete observability across your cloud environment. Skipping any single configuration creates blind spots, so we will review the exact CLI commands and retention policies you must memorize before attempting the certification exam. As you prepare for the AZ-305 exam, focus on distinguishing between metrics and log storage backends. You must know how to configure diagnostic settings to route resource logs to a log analytics workspace or event hubs. Remember that the Azure Monitor agent replaces the legacy agent for guest OS monitoring, so choose AMA in exam scenarios. Finally, always select the workspace option when the question requires correlating logs across multiple resources or performing advanced KQL queries. Misreading scenario keywords triggers incorrect answers, so we will practice the exact diagnostic phrases and service tier limitations you must recognize under timed conditions. Imagine you are navigating a busy highway at midnight with completely shattered windshields. That is exactly what managing cloud infrastructure looks like without proper telemetry. Azure Monitor provides the radar system, but your log analytics workspace serves as the central control tower where all metrics land and get organized. We will configure this critical component today so your environment remains visible, secure, and fully optimized for production workloads. We will begin by defining the core purpose of a log analytics workspace and how it functions as your central data hub. Next, we will dive into configuration details focusing on SKUs, retention policies, and daily data caps to manage costs effectively. Then, we will cover connecting data sources using diagnostic settings and the Azure Monitor agent. Finally, we will break down KQL query anatomy with a practical example and review security best practices for exam success. A log analytics workspace functions as a highly optimized analytical engine rather than simple passive storage. When telemetry enters the environment, Azure automatically parses, indexes, and partitions the data into tables specifically designed for rapid querying. This architecture enables the platform to process billions of rows per second without degrading performance. Understanding this underlying structure is absolutely critical because poorly structured queries will trigger timeout errors and severely impact your overall monitoring strategy. A log analytics workspace is a distinct Azure resource that serves as the exclusive repository for aggregated log data, metrics, and traces. Every telemetry stream must route directly to this specific environment before you can leverage alerting rules, create custom dashboards, or perform historical analysis. Failing to establish a properly configured workspace will completely block your ability to generate actionable insights or maintain compliance with enterprise auditing standards. When configuring your workspace, 4 specific properties dictate performance, cost control, and regulatory compliance. The SKU determines your pricing model and available features. Data retention controls exactly how long historical logs remain accessible before automatic deletion. The daily data cap establishes a strict ingestion limit to prevent runaway costs. Finally, the chosen region directly impacts query latency and data residency requirements for audit purposes. Selecting the appropriate pricing tier directly impacts your monthly expenditure and operational flexibility. The free tier strictly limits ingestion to 500 megabytes daily with a 7-day retention window, making it suitable only for temporary testing. The consumption tier operates on a standard pay-as-you-go model based on actual volume processed. Commitment tiers offer substantial discounts when you guarantee a specific daily throughput volume. We will execute the Azure Monitor Log Analytics workspace, create command, to provision a new environment within your target subscription. You must explicitly specify the per GB 2018 SKU and set the retention parameter to 90 days using standard CLI flags. After provisioning completes successfully, you will run an update command to enforce a 50 gigabyte daily quota. This strict cap prevents unexpected billing spikes during sudden log volume surges. Once your central repository is established, you must actively route telemetry from specific resources. Azure PaaS services like App Services and Key Vaults require diagnostic settings to stream logs directly into the target workspace. Virtual machines and hybrid servers rely on the modern Azure Monitor agent to collect richer guest-level metrics. Confusing these two methods will result in incomplete data collection and missed security alerts. The ingestion pipeline begins when a virtual machine executes the Azure Monitor agent to collect system logs and performance counters. This agent immediately forwards the captured telemetry to a data collection rule that acts as your routing configuration. The DCR then directs the traffic specifically to your log analytics workspace for indexing and storage. Bypassing this structured flow will cause data loss and break dependency chains. Kusto query language functions as a precise sequential pipeline where each operator filters or transforms raw telemetry before passing it forward. Every statement begins with a specific table reference followed by pipe characters that chain multiple operators together. Each segment performs a distinct action, such as filtering rows or calculating aggregates. Misplacing a single pipe will break the execution sequence and return empty result sets. We will execute a targeted query against the heartbeat table to identify offline systems. The statement filters specifically for Windows operating system types before summarizing the maximum timestamp generated per computer identity. An extend operator calculates the exact minutes elapsed since the last reported signal, followed by a filter clause that isolates records exceeding 5 minutes of inactivity. This sequence reliably detects agent failures. Consider this scenario carefully before selecting your answer. If you configure a daily data cap of 10 gigabytes on your workspace, ingestion will automatically pause the moment that exact threshold is reached. The data does not get deleted immediately. Ingestion simply halts for the remainder of the calendar day and resumes exactly at midnight. This mechanism protects your budget from runaway logging processes. Treat monitoring infrastructure as your primary operational safety net rather than a secondary afterthought. A properly calibrated log analytics workspace guarantees the continuous visibility required to detect performance degradation early and maintain strict regulatory compliance. You must invest significant time during the initial design phase to configure retention windows and access controls correctly. Skipping this step will inevitably lead to costly audit failures. Protecting your central repository requires strict enforcement of Azure RBAC at the resource level. You must assign roles like reader or contributor to control baseline access across the entire workspace. For highly sensitive datasets, implement table-level permissions to restrict visibility to specific authorized personnel only. Failing to apply least privilege principles will expose critical telemetry to unauthorized users and violate compliance mandates. We successfully navigated the core components required to build a robust monitoring foundation. You learned how the log analytics workspace functions as your central analytical engine and compared pricing tiers to optimize monthly expenditures. We configured retention limits and ingestion caps using standard CLI commands, mapped the complete data flow through collection rules, and practiced targeted KQL syntax for heartbeat analysis. These skills directly prepare you for production deployments. The AZ-305 certification heavily tests your ability to differentiate between free, per GB, and commitment SKU tiers. You must memorize that retention windows span from 30 to 730 days and understand exactly how daily ingestion caps trigger automatic pauses. Be prepared to quickly identify when diagnostic settings are appropriate versus the Azure Monitor agent. Mastering these distinctions will directly improve your scenario-based question accuracy. Imagine a massive library where every book is thrown randomly onto the floor. You might have all the information you need, but finding it is impossible. In cloud architecture, logs are those books, and log routing is the system that sorts, indexes, and delivers them to the right shelf. Without this structure, you face a data swamp that hides insights and risks compliance. Today, we will design a solution that ensures your logs flow efficiently from source to destination using Azure Monitor workspaces and managed identities, preventing costly audit failures during certification exams. Here is our roadmap for this lesson. We will start by breaking down the core components that make up a log routing pipeline. Next, we will explore common scenarios like SIEM integration and real-time analytics. Then, we will tackle critical design considerations such as scalability and cost optimization. Finally, we will look at practical Azure implementation patterns using diagnostic settings and Fluent Bit. Mastering these steps prevents misconfigured routing rules that waste hundreds of dollars in ingestion fees and leaves your environment blind to critical security events during live troubleshooting. Let's define the anatomy of a log routing solution. Every pipeline consists of 4 essential parts. First, you have log sources, which generate the raw data. Second, log collectors or agents gather this data near the source. Third, routers and processors filter, parse, and enrich the logs. Finally, destinations store or analyze the routed information. Understanding these roles is key to building a robust architecture. Misplacing any component breaks the telemetry chain, causing delayed incident response times that exceed your 2-hour service level agreement targets. Before we dive deeper, let's lock in a key definition. A log routing solution is the infrastructure and process responsible for collecting logs from diverse sources, transforming them as needed, and delivering them to designated destinations. This definition highlights that routing is not just about moving data. It involves transformation and delivery to specific targets like SIEMs or archives. Failing to apply proper JSON serialization during transformation breaks downstream parsing queries. forcing you to rebuild complex KQL dashboards from scratch during production outages. Visualize the data flow in a typical routing pipeline. The journey begins at the source, where an application or service generates events. These events are picked up by a collector agent. The agent forwards the data to a router, which applies filters and parsing rules. Finally, the processed logs are pushed to one or more destinations, such as a monitoring dashboard or a long-term storage account. Skipping buffer validation at each hop risks dropping critical trace IDs when throughput exceeds 50,000 records per second during peak deployment windows. Different business needs require different routing strategies. Here is a comparison of common scenarios. For centralized observability, you route to log analytics for quick search and visualization. For security, you send events to a SIEM like Microsoft Sentinel for threat detection. Compliance demands immutable storage in blob storage. And for real-time analytics, Event Hubs provides the streaming capability needed for immediate alerting. Mixing these pathways incorrectly triggers redundant ingestion charges that double your monthly operational expenditure while delaying critical alert thresholds beyond acceptable limits. Now, let's discuss the critical design considerations. When architecting your solution, you must prioritize scalability to handle traffic spikes. Reliability is non-negotiable. Use buffering and retries to prevent data loss. Security requires encryption and access controls. Finally, cost optimization is vital. Filter out noise early and use tiered storage to manage ingestion costs effectively. Ignoring these factors causes pipeline bottlenecks that overwhelm your managed instance, forcing manual intervention when automated scaling thresholds breach 20 concurrent connections per minute. Remember this principle. A well-designed log routing solution ensures that the right logs reach the right systems at the right time. If your logs are not routed effectively, you cannot derive insights, detect threats, or prove compliance. The value of logging lies entirely in its accessibility and usability. Neglecting this standard results in fragmented telemetry datasets that invalidate your audit reports and prevent automated runbooks from executing within the required 15-minute response window during critical infrastructure failures. Let's look at a practical Azure example using diagnostic settings. This ARM template configures routing for a specific resource. Notice the properties block. We specify the workspace ID for log analytics, storage account ID for archiving, and Event Hub authorization rule ID for streaming. The logs array enables all logs category group, ensuring comprehensive coverage across sources. Running Azure Monitor diagnostic settings create without validating identity permissions causes silent failures that drop 30% of platform logs during routine maintenance cycles. Quick check. Which component in the routing pipeline is responsible for filtering irrelevant logs and enriching them with context before they reach the destination? Is it the source, the collector, the router, or the destination? Take a moment to think about the roles we discussed. Selecting the wrong handler delays critical alert propagation by over 10 seconds, causing your automated remediation scripts to miss the exact timestamp when database connection pools finally exhaust their maximum capacity limits. For containerized environments, FluentBit is a powerful choice. This configuration snippet shows the input, filter, and output sections. The input uses the tail plugin to read container logs. The Kubernetes filter enriches logs with metadata. Finally, the Azure output sends the data to log analytics using the customer ID and shared key. Misconfiguring the flush interval parameter beyond 3 seconds creates massive backlog queues that overwhelm your orchestration layer when processing 50,000 log entries per minute. Let's recap the key takeaways. We covered the 4 core components: sources, collectors, routers, and destinations. We explored scenarios ranging from observability to compliance. We emphasized design considerations like scalability, security, and cost. And we saw how Azure Diagnostic Settings and FluentBit implement these concepts in practice. Mastering these patterns prevents costly misconfigurations that bypass regulatory retention policies and leaves your infrastructure vulnerable when automated backup routines fail during unexpected service disruptions. For the AZ-305 exam, focus on these points. You should know how to configure diagnostic settings for multiple destinations simultaneously. Understand the role of log analytics workspaces and event hubs in routing. Be prepared to identify when to use immutable storage for compliance. Finally, remember that cost optimization through filtering is a key design goal. Overlooking these specifics leads to incorrect answer selections on scenario-based questions, where you must calculate exact ingestion rates or troubleshoot failed IPI call responses during simulated outages. Imagine a commercial airliner taking off. During the flight, thousands of systems operate simultaneously. If an issue arises, pilots rely on the flight data recorder, capturing every critical data point from engine performance to cockpit conversations. In Azure, your resources face similar complexity. Diagnostic settings act as that black box, ensuring you capture essential logs and metrics needed to troubleshoot, secure, and optimize your cloud environment effectively before minor glitches become costly outages. In this lesson, we will cover the fundamentals of diagnostic settings. You will learn what they are and why they matter, dive into the difference between logs and metrics, compare destination options like log analytics and storage, and finally walk through a step-by-step configuration workflow using CLI commands and governance best practices to ensure your architecture passes certification exams and survives real-world scaling challenges. Let us start with the core definition. Azure Diagnostic Settings are the mechanism that defines where and what operational data should be exported from an Azure resource. Almost every service, from virtual machines to SQL databases, generates logs and metrics. These settings act as the conduit, allowing you to direct this data to external services for storage, analysis, or real-time streaming, preventing blind spots during critical security investigations. Diagnostic settings allow you to select specific categories of logs and metrics. Logs are event-driven records of actions, errors, and warnings that provide detailed context for specific events. Metrics are numerical values representing performance over time, like CPU usage or memory. While logs give you depth, metrics give you trends. Understanding this distinction is key to configuring the right data for your needs and avoiding unnecessary storage costs. Now let us look at where this data can go. You have several destination options. Log Analytics is the recommended choice for most enterprise monitoring, offering powerful KQL querying and integration with alerts. Storage accounts are ideal for long-term archival of audit logs where immediate analysis is not required. Event hubs provide low-latency streaming for real-time processing or third-party SIEM tools, ensuring you match the right sync to your compliance requirements. Here is how the data flows. Your Azure resource generates logs and metrics. Diagnostic settings capture this data. From there, the data is routed to your chosen destinations. It might go to log analytics for querying, storage for archiving, or event hubs for streaming. This flow ensures that every piece of operational data reaches the right place for analysis, preventing critical performance bottlenecks from going unnoticed during peak traffic hours. Now let us configure diagnostic settings. We will follow a 3-step workflow. First, identify the resource and workspace. You need the resource ID of the target resource and the workspace ID of your log analytics workspace. These identifiers are mandatory for the CLI command to route data correctly, preventing misdirected logs that waste storage budget and delay incident response during critical failures. Let us see this in the Azure CLI. First, we retrieve the Log Analytics Workspace ID using the show command and query the ID field. Then, we get the resource ID for our app service. These IDs are essential inputs for the configuration command, ensuring accurate routing and preventing configuration drift that breaks alerting pipelines during active security investigations. Next, we select the logs and metrics. For an app service, common choices include HTTP logs, console logs, audit logs, and platform logs. You will also want to enable all metrics for performance tracking. Selecting the exact categories prevents unnecessary egress fees while guaranteeing you capture the specific telemetry required for compliance audits and rapid root cause analysis during production incidents. Now we run the create command. We specify the name, resource, and workspace IDs. For logs, we pass a JSON array with categories like HTTP logs and console logs, setting enabled to true. Similarly, we add all metrics to the metrics array. This precise syntax ensures your telemetry pipeline activates immediately, preventing silent failures that obscure performance degradation during peak load testing. Finally, we apply and automate governance. Manual configuration is highly error-prone at scale. Use Azure Policy to enforce diagnostic settings across subscriptions or ARM templates for infrastructure as code. This ensures consistency and compliance, preventing orphaned resources from slipping through security audits while standardizing operational visibility across every engineering team and eliminating costly manual remediation efforts. Here is an ARM template snippet for automation. The resource type is Microsoft. Insights diagnostic settings. We define the workspace ID in properties and specify logs with categories like HTTP logs and retention policies. This ensures every deployed resource has diagnostics configured consistently, preventing configuration drift that breaks monitoring pipelines during automated deployment cycles and guarantees audit readiness across all environments. Remember this principle: governance ensures consistency. Never rely on manual configuration for scale. Use Azure Policy or ISC to enforce diagnostic settings, preventing drift and ensuring compliance across your environment. This approach guarantees that every subscription meets regulatory standards while eliminating the operational overhead of tracking individual resource configurations manually during high-pressure incident response scenarios. Let us check your understanding. Which destination is best for long-term archival of audit logs where immediate querying is not required? Is it log analytics, storage account, or event hubs? The correct answer is storage account, as it offers cost-effective tiering and compliance retention policies that prevent expensive data egress during routine historical reviews. To recap, diagnostic settings define where and what data is exported. Logs provide detailed events. Metrics show trends. Destinations include log analytics for querying, storage for archiving, and event hubs for streaming. Configure via CLI or ARM and govern with policy for consistency. Mastering these components ensures reliable telemetry collection that directly supports certification success and production stability. For the AZ-305 exam, focus on choosing the right destination based on requirements. Know log analytics for operational monitoring, storage for archival, and event hubs for streaming. Understand CLI commands for configuration and ARM templates for automation. Governance with policy is also a key topic. Mastering these scenarios will directly improve your ability to design secure, observable architectures. Imagine flying a plane through a storm with no instruments. You have no idea how fast you are going, what your fuel levels are, or if the engines are failing until it is too late. That is exactly what building a production application without monitoring feels like. As solution architects, we cannot afford blind spots. In this lesson, we will configure auto-collection for HTTP requests and set retention to 90 days to prevent costly downtime during peak traffic. Here is our roadmap for the next few minutes. We will start by understanding why Application Insights is a strategic tool for architects, not just developers. Then we will look at core telemetry types like requests and dependencies. Next, we will walk through instrumenting an ASP.NET Core app using the Azure CLI Azure Monitor App Insights component. Finally, we will cover adaptive sampling to control costs and prepare you for the AZ-305 exam, ensuring you avoid costly production outages. Application Insights is an extensible application performance management service within Azure Monitor. It helps you monitor live web applications and includes powerful analytics tools to diagnose issues and understand user behavior. For architects, it shifts you from reactive debugging to proactive problem detection. You can catch latency spikes over 500 milliseconds before they impact users significantly, ensuring you maintain strict service-level objectives rather than waiting for angry customer tickets to pile up. Let's define a key term you will encounter frequently: Application Performance Management. IPM is a discipline that uses tools to monitor and manage the performance and availability of software applications. In the Azure ecosystem, Application Insights serves as your primary IPM tool. It automatically detects performance anomalies under 200 milliseconds and provides deep insights into user interactions, preventing cascading failures when traffic suddenly spikes during peak hours. To design a monitoring strategy, you need to understand the different telemetry types Application Insights collects. Requests track HTTP calls, including response times and success rates. Dependencies record calls to external services like Azure SQL or REST APIs. Exceptions capture unhandled errors with full stack traces. Tracking dependencies under 150 milliseconds helps you isolate slow database queries early. Now let's look at how to implement Application Insights in a real application. We will follow a three-step procedure to instrument an ASP.NET Core app. First, you provision the Application Insights resource using the Azure Portal or CLI. You will run Azure Monitor App Insights component create to establish the backend workspace. Missing this step leaves your system completely unobservable, risking undetected downtime during critical deployments. Here is the exact Azure CLI command to create the resource. We specify the resource group named Prod West US2 and the region Eastus, while setting the application type to web. This command provisions the backend component ready to ingest data. You must note the generated connections string immediately, as losing it requires manual regeneration and breaks your telemetry pipeline during active development. Next, we add the SDK and configure the application environment. You install the Microsoft Application Insights ASP.NET Core NuGet package and then configure telemetry directly in Program CS. This step wires up the automatic collection of requests, dependencies, and exceptions without requiring manual instrumentation for every single endpoint call. Skipping this configuration leaves your code blind to actual runtime behavior and masks underlying infrastructure issues. In Program CS, we first register the telemetry services using Add Application Insights Telemetry. The configuration enables adaptive sampling to manage data volume and ensures dependency tracking remains active for all outgoing calls. This code snippet shows exactly how you wire up the SDK with specific options to control what gets collected, preventing unnecessary storage costs while preserving critical diagnostic data for troubleshooting. Finally, we manage the connection string and verify the incoming data stream. The connection string is stored securely in app settings, JSON, or injected via environment variables. This critical link connects your application code directly to the Azure resource you created. Once deployed, you can view live metrics and query logs using KQL in the Log Analytics workspace, ensuring you catch deployment failures immediately. Here is the exact configuration in app settings, JSON. We define the connection string containing the instrumentation key and ingestion endpoint URL. This JSON block ensures the application authenticates correctly and sends telemetry to the designated resource. For production environments, you must rotate this secret regularly using Azure Key Vault to prevent unauthorized data exfiltration during a security audit. As an architect, you must carefully balance deep observability with strict cost controls. Application Insights uses sampling to reduce data volume while maintaining statistical accuracy. Adaptive sampling is the default approach. It automatically adjusts the sample rate based on real-time traffic load. You should also configure data retention policies to exactly 90 days, preventing unexpected billing spikes during high-traffic campaigns. Remember this principle clearly. Observability is never an afterthought. You must design for it from the very first sprint. If you do not instrument your application with the right telemetry, you will be completely flying blind when latency spikes or service dependencies fail in production. Proper instrumentation saves thousands of dollars in emergency troubleshooting and prevents massive customer churn. Let's quickly check your understanding before we move forward. Which sampling method is officially recommended for most production applications to automatically reduce data volume while preserving statistical accuracy? Is it fixed-rate sampling, adaptive sampling, or disabling sampling entirely? Choosing the wrong option will either drain your budget or leave you without critical diagnostic logs during an outage. To recap, Application Insights serves as your primary IPM tool for monitoring live applications at scale. You should provision the resource, add the SDK, and configure the connections string to instrument your app effectively. Always enable adaptive sampling to manage costs and focus exclusively on business-critical paths for instrumentation, ensuring you catch revenue-impacting errors before they reach end users. For the AZ-305 exam, focus heavily on the differences between telemetry types and their specific use cases. You may be asked about adaptive sampling strategies or how to secure connection strings using Key Vault. Remember that Application Insights stores data in a log analytics workspace, so you will frequently encounter KQL queries testing your ability to filter custom events efficiently. Imagine you're driving a car at night without headlights. That's exactly what running production infrastructure without telemetry feels like. You cannot see hazards or verify your path, risking catastrophic failure. In Azure, Network Watcher provides the essential radar for your virtual networks. This regional service deploys agents to monitor every packet and connection, enabling you to diagnose latency, enforce security policies, and ensure compliance before users report outages. We begin by defining the regional scope of Network Watcher and how agents deploy automatically when you enable the service in a target location like East US. Next, we walk through the implementation chain, enabling the service, configuring NSG flow logs with retention policies, and linking traffic data to log analytics workspaces. Finally, we review exam-critical distinctions between tools like IP flow verify versus packet capture to help you pass the AZ-305 assessment confidently. Azure Network Watcher is a regional service that provides diagnostic tools to monitor and troubleshoot IaaS resources within your virtual networks. When you enable the service in a region such as West Europe, Azure automatically deploys monitoring agents to collect telemetry data from supported resources like VMs and NICs. This capability is essential for validating traffic flow, auditing security group rules against compliance standards, and proactively identifying connectivity issues before they escalate into critical production outages affecting your users. Network Watcher includes distinct features tailored to specific troubleshooting scenarios. Use topology to visualize resource dependencies and connections within a VNet. Employ Connection Monitor to track end-to-end latency and availability between endpoints over time. Utilize IP Flow Verify to check if a specific packet is allowed or denied by NSG rules. Deploy NSG flow logs to record all traffic passing through a security group, and use packet capture for deep packet inspection of network payloads. Implementing network monitoring follows a strict procedural chain to ensure full visibility. First, you must enable the Network Watcher service in the target region using the Azure CLI or portal. This action creates the management resource and triggers automatic agent deployment across all supported resources in that scope. Without this foundational step, subsequent tools like flow logs or connection monitors cannot function, leaving your infrastructure blind to traffic anomalies and security violations. Run the following Azure CLI command to enable Network Watcher in your target region. Use as Network Watcher, create resource group MyRG, location EasTIS2. This command provisions the service and triggers automatic agent deployment for all virtual networks in East US2. Ensure you specify the correct resource group and location. Otherwise, the monitoring agents fail to deploy, and you cannot access diagnostic tools for resources within that region during an incident. With the service enabled, proceed to configure specific diagnostic tools based on your architectural requirements. For instance, enable NSG flow logs to capture granular traffic data for security auditing and compliance reporting. Alternatively, configure Connection Monitor to establish baseline metrics for end-to-end latency between application tiers. Selecting the appropriate tool ensures you gather relevant telemetry without incurring unnecessary storage costs or overwhelming your log analytics workspace with excessive data volume. This PowerShell command configures NSG flow logs for a specific security group. Use Enable as Network Watcher flow log target resourced subscriptions, resource groups /MyRG /providers /Microsoft, network security groups MyNSG, and specify a storage account with a 7-day retention period. You can also route logs directly to a log analytics workspace named SecOps Workspace. This configuration captures all allow and deny decisions, providing critical visibility into traffic patterns while ensuring you retain data long enough for forensic analysis during a security investigation. The final implementation step integrates collected telemetry with Azure Monitor and a log analytics workspace for advanced analysis. Routing flow logs to a workspace enables you to write custom KQL queries, build performance dashboards, and configure automated alerts based on specific thresholds. For example, trigger an alert when denied traffic spikes by 20% within an hour. This integration transforms raw log data into actionable insights that support rapid incident response and continuous compliance monitoring. Execute this KQL query within Log Analytics to analyze NSG flow logs for security events. Use Azure Diagnostics, where category == network security group event and action == deny summarize count == count by rule name, source address. This query filters specifically for denied traffic and groups results by the blocking rule name and source IP address. It allows you to quickly identify misconfigured rules blocking legitimate application traffic, or detect potential brute force attacks originating from external sources. NSG flow logs capture detailed metadata for all IP traffic traversing a network security group. Each log entry records the source and destination IP addresses, port numbers, protocol type, and the specific allow or deny decision applied by the rule. You can store this data in a standard storage account or stream it directly to log analytics using the Microsoft Insights Logs table. This granularity is essential for auditing access patterns, troubleshooting connectivity issues, and validating security posture against regulatory requirements. Run this command to enable NSG flow logs with traffic analytics enabled for enhanced visualization. Specify the NSG resource ID and a storage account, then set retention 7 days. Adding Traffic Analytics Interval 10 enables automatic processing into rich visualizations within log analytics. This feature aggregates flow data to highlight top talkers and traffic patterns, making it significantly easier to spot anomalies like bandwidth spikes or unexpected communication paths that indicate a misconfiguration or compromise. Test your knowledge with this scenario. You need to determine if a specific packet is allowed or denied by NSG rules for a VM without capturing the full traffic stream. Which tool do you use? Is it packet capture, IP flow verify, or topology? Consider that packet capture records actual packets, while topology shows resource maps. The correct answer is IP flow verify, which queries the effective security group rules to evaluate packet flow against policy configurations instantly. Remember this core principle. Effective monitoring goes beyond detecting failures and focuses on understanding baseline behavior. Network Watcher tools help you visualize traffic flows and identify performance trends before they escalate into critical issues. By proactively analyzing connectivity metrics and security events, you ensure your infrastructure remains secure, performant, and compliant with organizational standards. This proactive approach reduces mean time to resolution and prevents minor anomalies from disrupting production workloads for your end users. The monitoring data flow begins when traffic traverses a network security group, generating flow logs that are routed to log analytics for storage and analysis. Simultaneously, Network Watcher tools operate independently. IP flow verify queries NSG rules directly to validate packet decisions, while Connection Monitor executes synthetic tests between endpoints to measure latency and availability. This combined approach ensures comprehensive visibility, allowing you to correlate traffic patterns with connectivity health and quickly isolate the root cause of network issues. We have covered the essentials of Azure Network Watcher, including its regional scope and key features like topology and NSG flow logs. You implemented a monitoring solution by enabling the service, configuring tools with specific retention policies, and integrating data into log analytics workspaces. NSG flow logs provide detailed traffic metadata for auditing, while Traffic Analytics offers rich visualizations of top talkers. Use these capabilities to maintain strict visibility, enforce security controls, and ensure reliable network performance across your cloud environment. For the AZ-305 exam, focus on distinguishing use cases for each Network Watcher tool. Know that IP flow verify checks rule effectiveness instantly, whereas packet capture records actual packets for deep inspection. Understand that Network Watcher is a regional service and must be enabled separately in each region where you deploy resources. Be prepared to select the correct tool for connectivity troubleshooting or traffic analysis scenarios. Practice configuring these features via CLI or PowerShell to reinforce your practical knowledge. Imagine a smoke detector in your home. It does not just sit there watching the air. It listens for a specific condition and immediately triggers a loud alarm to wake you up. In Azure, your applications need that same proactive guardian. Simply collecting logs is passive. True reliability comes from defining conditions that automatically trigger responses when things go wrong. Today, we will master Azure Monitor alerts and action groups to build that automated safety net before a production outage costs you revenue. Here is our roadmap for this lesson. We will start by breaking down the core fundamentals and the different types of alerts available in Azure Monitor. Next, we will dive into action groups, which are the engine behind every alert response. Then we will walk through a hands-on procedure for creating an action group using the Azure Monitor Action Group CLI command. Finally, we will cover best practices and specific exam tips to ensure you can configure these solutions confidently without missing critical scoring points on the certification. Let us look at the alert landscape. Azure Monitor provides a unified experience for monitoring resources, but it supports 5 distinct signal types to cover every scenario. Metric alerts watch numeric values like CPU usage on virtual machines. Log alerts query your workspace using KQL queries. Activity log alerts track subscription events like role changes. Smart Detection uses AI to find anomalies in application insights web apps. And Prometheus alerts handle open-source metrics. Understanding which signal type matches your data source prevents missed critical failures and saves troubleshooting time. An alert rule is only half the story. You need to know what happens when it fires. Action groups serve as a reusable collection of notification preferences and automated actions that any alert can call upon. Instead of hard-coding email addresses into every single alert, you define the action group once and link it to multiple rules using the Azure Monitor Action Group Create command. This ensures consistent communication and rapid response across your entire environment, while preventing duplicate notifications during major outages. Visualize the flow of data when an alert triggers. First, the monitoring service collects metrics or logs from your resource every 15 seconds. Second, the evaluation engine checks these values against your defined conditions at a set frequency. Third, if the condition is met, the alert fires and immediately invokes the linked action group. Finally, the action group distributes the notification via email, SMS, or triggers an automation workflow like a logic app. This pipeline ensures no critical event goes unnoticed during peak traffic hours. Now let us get practical. We will create an action group step by step using the Azure CLI. First, we define the name and resource group to organize it properly in your subscription. Second, we add immediate notifications like email or SMS for quick awareness. Third, we wire up advanced integrations like webhooks or logic apps for automated remediation. Follow along as we build this structure to prevent manual response delays during production incidents. We start by running the create command in your terminal. We specify the resource group and give the action group a descriptive name like High CPU Action Group. We also provide a short name for quick reference in dashboards. This command creates the container that will hold our notifications. Notice we are not adding actions yet. We just establish the foundation to avoid configuration errors during later integration steps. With the container created, we add our first layer of communication. We define email recipients and SMS numbers to ensure key personnel are alerted immediately. This step focuses on direct human notification before any automation kicks in. You will use the Azure Monitor Action Group Notification command to attach these channels securely, ensuring your on-call engineers receive critical alerts without delay during service disruptions. We extend our action group by adding notifications directly through the terminal. The command uses the actions parameter with the email type to specify recipients like ops at Contoso. COM. You can add multiple action definitions in one call using JSON arrays. This ensures that if a metric alert fires, an email is sent instantly to the ops team without writing custom code, preventing alert fatigue from duplicate manual emails. Finally, we wire up advanced integrations directly in the CLI. This is where monitoring becomes automated. We configure webhooks to call external systems or logic apps to trigger complex remediation workflows, like scaling virtual machine scale sets. This step transforms a simple notification into an active response mechanism that reduces mean time to resolution during critical infrastructure failures. We complete the setup by adding a webhook action through the CLI. The command specifies the HTTP endpoint URL where the alert payload should be sent securely. This allows you to integrate with third-party tools like Slack or ServiceNow for ticketing. Now your action group is fully operational and ready to link to any alert rule, ensuring automated workflows execute reliably without manual intervention. Let us compare the primary alert types to help you choose the right one. Metric alerts are best for numeric thresholds like CPU or memory usage on VMs. Log alerts are ideal for querying specific error patterns using KQL in a workspace. Activity log alerts track administrative events and subscription health. Smart Detection handles AI-driven anomalies for web apps. Use this grid to match your monitoring goal to the correct signal type, preventing misconfigured thresholds that waste cloud spend. Keep this principle in mind as you design your monitoring strategy. An alert without an action group is just a notification that no one acts on. Always pair every alert rule with a clear, tested response mechanism to minimize downtime and ensure your team can react instantly. Configure severity levels properly so critical outages automatically trigger escalation procedures rather than relying on manual email checks during peak hours. Let us check your understanding. You need to alert the team when a specific error message appears in Application Insights logs. Which signal type should you use, and what component defines the email recipients? Think about the data source and the response mechanism carefully. Log alerts paired with action groups will solve this scenario, ensuring you avoid false positives that overwhelm engineering teams during routine maintenance windows. We have covered the essentials of Azure Monitor alerts. You learned the 5 signal types and how to choose between metrics, logs, and activity events. You defined action groups as reusable response engines and walked through creating them with CLI commands for notifications and integrations. Finally, you compared alert types and tested your knowledge. These skills form the backbone of proactive cloud monitoring, preventing unmanaged resource costs during unexpected traffic spikes. For the AZ-305 exam, focus on these critical points. You must know how to link an alert rule to an action group using the resource ID in CLI or ARM templates. Understand that action groups are subscription scoped but can be shared across resources. Remember that Smart Detection is automatic for Application Insights web apps. Finally, expect questions on alert severity levels and how they prioritize responses during outages, ensuring you pass configuration scenarios without manual errors. Imagine sitting in the cockpit of a modern jet. The pilot relies on curated gauges for immediate status, not raw sensor logs. If a warning flashes, they drill into detailed diagnostics to find the root cause. Azure Monitoring demands this exact separation between situational awareness and deep investigation. We will master workbooks and custom dashboards today. Build interfaces that deliver precise insights when needed. Skip this distinction, and your team drowns in noise while critical failures slip past unnoticed. Here is our roadmap for this lesson. We will start by exploring Azure workbooks, focusing on how they handle KQL queries and dynamic parameters. Next, we will configure custom dashboards for quick operational views. Then we will compare these two tools side by side to clarify exactly when to use each one. After that, we will examine integration patterns that link dashboards directly to workbooks. Finally, we will walk through deploying dashboards programmatically using ARM templates. Mastering this sequence prevents configuration drift and ensures your monitoring architecture scales reliably. Azure Workbooks are your primary tool for interactive data exploration and reporting. Unlike static charts, a workbook provides a flexible canvas where you combine text, analytics queries, metrics, and parameters into one document. This makes them versatile for troubleshooting guides and operational reports. You can query multiple sources like log analytics and resource graph, then visualize results in grids or time charts. The key advantage is interactivity. Users filter data dynamically without editing underlying queries. If you skip parameterization, your team wastes hours manually adjusting time ranges during critical incidents. Before we dive deeper, let's define a key term that often causes confusion. A custom dashboard is a consolidated, personalized view of your cloud resources and monitoring data. While workbooks handle deep analytical dives, dashboards are optimized for high-level overviews and quick access to critical information. They act as the executive summary or team status board. This layout provides a snapshot of health and performance at a glance, making it ideal for operations managers who need immediate awareness. Skipping this distinction results in cluttered screens that hide critical alerts during peak load. Let's look at a practical example of building a workbook to monitor VM performance. We start by adding a time range parameter, allowing users to select the data window dynamically. Next, we add a resource picker parameter to filter by specific virtual machines. Then we write a KQL query that pulls performance counter data, filtering for CPU utilization and summarizing it over 5-minute intervals. Finally, we render this as a time chart. Forgetting to set default values will force every user to manually configure filters before viewing any data. Now let's compare workbooks and custom dashboards side by side to clarify their distinct roles. Workbooks excel at interactive analysis, allowing you to combine multiple data sources and drill down into root causes. They are perfect for troubleshooting guides and security investigations. Dashboards focus on high-level overviews and quick access. They are ideal for executive summaries where you need a consolidated view of key performance indicators. Understanding this distinction helps you design the right solution for your audience. Mixing them up will cause unnecessary licensing costs and slow down incident response times. Dashboards and workbooks are complementary tools. A common pattern is to use a dashboard for a high-level overview, with tiles that link directly to detailed workbooks for deeper analysis. For example, an application health tile displays current metrics, but includes a hyperlink to a workbook where engineers perform root cause analysis. This flow allows operations teams to quickly identify issues and seamlessly transition to investigative mode. Breaking this link forces your team to manually search for resources instead of clicking through to diagnostics. Let's walk through the process of deploying a dashboard programmatically using an ARM template. This ensures consistency and version control across environments. First, we define the schema and parameters for the deployment. Next, we configure the lenses and parts to specify the tiles and their layout. Finally, we deploy the template to the target resource group. We will explore each step in detail with code examples. Skipping validation steps will cause deployment failures that break your monitoring pipeline during critical release windows. Here is the first step, defining the schema and parameters. We start with the JSON schema for a deployment template. Then we add parameters for the dashboard name and location, setting defaults to make reuse easier. This structure allows you to parameterize your dashboard configuration, making it adaptable across different environments like dev, test, and production. Incorrectly naming the resource group will cause immediate deployment failures that block your entire monitoring rollout. Now we move to the second step, configuring the lenses and parts. This is where you define the actual tiles, their positions, and the data they display. You specify the resource IDs, metrics, and time context for each tile. This configuration determines what information appears on the dashboard and how it is presented. Mismatching metric namespaces will render empty charts that confuse your operations team during daily stand-ups. In this example, we configure a metric chart tile for CPU utilization. We specify the resource ID, metric namespace, and aggregation type. We also define the time context to show data from the last 4 hours with 5-minute granularity. This JSON structure precisely defines the tile's behavior and appearance within the dashboard. Forgetting to set the correct aggregation type will generate inaccurate graphs that mislead your capacity planning decisions. Finally, we deploy the ARM template to the target resource group. This step provisions the dashboard in Azure and makes it available to users. You can use the Azure CLI or PowerShell to execute the deployment command, passing the template file and parameter values. This completes the programmatic creation of your dashboard. Running this without checking dependency order will cause silent failures that leave your monitoring infrastructure incomplete during active deployments. Here is the CLI command to deploy the dashboard. You specify the resource group name and the template file location. This command reads the JSON definition and creates the dashboard in Azure, applying all the configured tiles and settings. Once deployed, the dashboard is ready for users to access and interact with. Adding extra flags will trigger unexpected overwrites that erase your carefully designed tile layouts. Remember this principle as you design your monitoring solutions. Dashboards show the status. Workbooks reveal the cause. Use dashboards for quick situational awareness and workbooks for deep investigative analysis. This distinction ensures your team can respond quickly to alerts while having the tools necessary to resolve complex issues. Ignoring this separation will create redundant reports that waste storage quotas and confuse your incident response workflow. Let's check your understanding. You need to provide a real-time health overview for a team of operations managers who need to see key performance indicators at a glance. Which tool is best suited for this requirement? Is it a workbook or a custom dashboard? Think about the primary use case and interactivity level required. Choosing the wrong interface will delay critical decisions because the team struggles with unnecessary query editors instead of viewing immediate metrics. We have covered the essential aspects of workbooks and custom dashboards. Workbooks offer flexible, interactive analysis with KQL queries and parameters, making them ideal for troubleshooting. Custom dashboards provide consolidated views for quick status checks and executive summaries. We compared their features to clarify when to use each tool. We also explored integration patterns that link dashboards to workbooks for a seamless workflow. Finally, we walked through the ARM deployment process to programmatically create dashboards. Skipping this review will cause you to misconfigure monitoring architectures during your certification exam. For the AZ-305 exam, focus on knowing when to use workbooks versus dashboards. Expect questions about designing monitoring solutions that require both high-level overviews and deep investigative capabilities. Pay attention to keywords like interactive analysis, troubleshooting guides, and quick status checks. Also, be familiar with the ARM template structure for deploying dashboards, including schema and tile configuration. Missing these details will cost you points on architecture design questions, where precise tool selection matters most. Imagine driving a car at night with no headlights and a dashboard that only lights up when the engine explodes. That is exactly what it feels like to manage a production system without a solid monitoring strategy. In this lesson, we will design a comprehensive approach using Azure Monitor to give you visibility into performance, reliability, and security before issues impact your users. We are moving from reactive firefighting to proactive control, ensuring you understand not just if something breaks, but why it happens. Here is our roadmap for mastering this topic. We will start by defining the golden signals that every SRE practitioner must track. Next, we will explore monitoring layers from infrastructure to business outcomes using Azure Monitor workspaces. We will compare proactive synthetic checks against reactive threshold alerts to find the right balance. After that, we will walk through a step-by-step implementation process with real code examples. Finally, we will cover alerting strategies to ensure your team acts on data effectively without causing downtime. Let's define a core concept you will see repeatedly in the exam: the golden signals. These are 4 key metrics recommended by Google SRE to monitor any user-facing system. You must track latency, traffic, errors, and saturation across every service. By focusing on these specific areas, you can detect performance degradation early before customers experience checkout failures. Missing any single signal leaves blind spots that directly cause revenue loss during peak traffic windows. A comprehensive strategy must cover multiple layers of your stack because no single tool gives the full picture. Infrastructure monitoring tracks virtual resources like CPU and disk I/O using Azure Monitor metrics. Application monitoring dives into code-level performance through request rates in application insights. Business monitoring connects technical metrics to outcomes like login success rates in Power BI. Each layer provides unique insights that help you pinpoint root causes before a cascading failure takes down your entire environment. When designing your strategy, you must choose between proactive and reactive monitoring approaches. Reactive monitoring triggers alerts after a problem occurs, which is common but can lead to direct user impact. Proactive monitoring aims to detect issues before they affect users, using techniques like synthetic availability tests in application insights. The exam often tests your ability to select the right approach based on the scenario. Use reactive for simple thresholds and proactive for complex reliability requirements to prevent customer churn. Now let's look at how to implement this strategy step by step. We will start with the first phase of the process, which involves defining your signals and layers using Azure Monitor workspaces. You must map each golden signal to a specific data source before writing any code. Skipping this mapping phase causes fragmented dashboards that waste engineering hours during critical incident response windows. In this first step, you instrument your application to capture the golden signals using a C# snippet for ASP.NET Core. We register the application Insights SDK to automatically capture requests and dependencies via the Add Application Insights method. Then, we add health checks to monitor service availability against a 99% SLI target. This code ensures that metrics flow into Azure Monitor without manual intervention, preventing silent database connection pool exhaustion during traffic spikes. With signals defined, we move to the second step, instrumenting services and infrastructure by configuring the Azure Monitor agent across your environment. You must deploy the VM Insights extension to every virtual machine in your scale set. Failing to install this agent leaves critical disk queue length metrics uncollected, which directly prevents you from detecting storage bottlenecks before application timeouts occur. For infrastructure monitoring, you can use Azure CLI to create a metric alert rule targeting high CPU usage on a virtual machine. Run as monitor metrics alert create with the resource group, percentage CPU metric name, and threshold above 80%. The window size defines how long the condition must persist before firing. This automated approach ensures immediate notification, preventing cascading service failures that trigger costly auto-scale penalties. The final step is configuring alerts and dashboards to visualize the data using Azure Portal widgets. You must link each dashboard to a specific log analytics workspace to guarantee consistent data filtering. Neglecting this configuration step causes delayed incident response times because engineers waste valuable minutes navigating between disconnected telemetry sources during active outages. To visualize logs and traces, you can use KQL queries in Azure Log Analytics to filter traces by error severity. This query projects the timestamp, message, and operation ID while filtering for status codes above 400. You can embed this query in a dashboard widget to get a real-time view of errors. This allows developers to quickly identify issues without digging through raw files, preventing prolonged customer-facing downtime during peak hours. Let's look at the data flow in a monitoring architecture where data originates from applications, infrastructure, and platform logs. These sources send telemetry to collectors such as Azure Monitor or log analytics workspaces. The storage layer retains the metrics and logs for analysis using default retention periods. Finally, visualization tools consume this data to provide insights to your team. This pipeline ensures seamless flow, preventing data loss that would otherwise obscure critical performance trends. A critical principle to remember is combating alert fatigue through strict notification hygiene. Too many non-actionable alerts desensitize your team, causing them to ignore critical warnings during active incidents. Focus on actionable alerts that truly indicate a problem requiring immediate intervention. Aggregate noisy alerts using Azure Monitor smart detection rules to keep notifications meaningful and prevent engineer burnout during extended outages. Let's check your understanding with a quick certification question. Which golden signal measures how full your service is, such as CPU utilization or memory usage? Is it latency, traffic, errors, or saturation? Think about which metric directly relates to resource capacity limits. Selecting the wrong signal during an exam scenario will cause you to misdiagnose performance bottlenecks and miss critical scaling requirements. When configuring alerts, you have two main strategies: threshold-based and baseline anomaly detection. Threshold-based alerting uses static limits, such as CPU greater than 80%. This is simple, but causes false positives during normal traffic spikes. Baseline anomaly detection learns normal behavior patterns in application insights and alerts on statistical deviations. This reduces noise and catches issues that do not fit a fixed threshold, preventing missed critical failures during unexpected load changes. We have covered the key aspects of designing a comprehensive monitoring strategy using Azure Monitor. You learned about the golden signals, latency, traffic, errors, and saturation across every service tier. We explored monitoring layers from infrastructure metrics to business outcomes. You saw how to implement the strategy with code examples for instrumentation and automated alerts. Finally, we discussed alerting strategies to prevent fatigue, ensuring reliable performance during production deployments. For the AZ-305 exam, focus on selecting the right monitoring tools for different scenarios involving application, insights versus log analytics. You may be asked to choose between synthetic web tests and metric alerts based on data type requirements. Remember that synthetic monitoring is proactive, while threshold alerts are reactive. Practice identifying the golden signals in code snippets to avoid misconfiguring critical production environments and failing scenario-based questions. Imagine driving a high-performance vehicle through dense fog without headlights or dashboard gauges. That is exactly what running production workloads without a solid identity strategy looks like. In cloud architecture, Microsoft Entra ID serves as your unshakable foundation. Without it, applications leak data and misconfigured permissions cascade into compliance failures. We will explore how to architect secure access controls that keep your Azure ecosystem resilient and audit-ready. Here is our roadmap for this lesson. We will start by defining the tenant and core components that make up your identity landscape. Next, we will examine managed identities to eliminate hard-coded client secrets in production code. Then we will compare authentication methods using a reference table tailored for AZ-305 scenarios. After that, we will walk through registering an application with exact CLI parameters. Finally, we will cover hybrid identity strategies to securely bridge on-premises directories without exposing sensitive credentials. Let's define the most fundamental object, the tenant. A tenant is your dedicated, isolated instance of Microsoft Entra ID acting as a secure boundary for all directory data. It hosts users, groups, and applications within a unique tenancy identifier like Contoso on Microsoft.com. Every Azure subscription must link to exactly one tenant to enforce isolation. Failing to map subscriptions correctly will cause cross-tenant access violations and break resource delegation entirely. Beyond the tenant boundary, you must master 3 core objects for certification success. Users and groups handle human access and role assignments efficiently. Application registrations define metadata like redirect URIs and OAuth scopes for developer tools. Service principals act as the actual identity instance within your directory, enabling secure IPI calls. Confusing these objects during deployment will trigger authorization errors and block automated deployments entirely. Managed identities are absolutely critical for cloud architects designing secure workloads. They allow Azure resources to authenticate seamlessly without storing credentials in source code or configuration files. Run the command as web app identity assign to link your app service to Entra ID automatically. This eliminates hard-coded client secrets and prevents credential rotation failures that commonly cause deployment pipeline breakage in production environments. When designing authentication, you must select the precise method that matches your security posture. Multi-factor authentication requires a second verification step, like an authenticator app, to block unauthorized access. Single sign-on streamlines workflows by allowing one login across multiple enterprise apps. Passwordless approaches eliminate text passwords entirely to drastically reduce phishing risks and help your team meet strict compliance audit requirements. Visualize the standard OAuth2 flow to understand exactly how these components interact. The process begins when a user requests a protected IPI endpoint. The application redirects the browser to Entra ID for credential verification and policy evaluation. Once verified, Entra ID issues a JSON web token back to your app. Failing to validate the token signature will allow unauthorized data access and violate security baselines. Now let's examine the exact procedure for registering an application in your directory. This is a frequent exam scenario and daily administrative task for cloud architects. We will break this workflow into 3 sequential steps. First, we create the app registration to define its metadata and supported account types before configuring any access controls. Here is the exact PowerShell command to provision your application object. We specify the display name and explicitly set the sign-in audience to Microsoft Entra ID organizations only. The web redirect URI points to your backend endpoint for handling authentication responses. Running this correctly creates the identity object without exposing public endpoints to unauthenticated traffic. With the base registration complete, we move directly to the second critical step. You must explicitly grant the application's specific delegated permissions to access external APIs like Microsoft Graph. This configuration defines exactly what data the app can read or write once it successfully acquires an access token from the authorization endpoint. This command explicitly grants delegated permissions to the Microsoft Graph API endpoint. You provide the target application identifier and append the exact permission ID you want to add to the manifest. Configuring these scopes correctly ensures your backend services can only read user profiles without accidentally requesting administrative write access that could compromise tenant integrity. The final configuration step requires granting explicit admin consent for all delegated permissions. For delegated scopes, tenant administrators must manually approve these requests before any end users can successfully sign in. Skipping this approval will cause immediate token rejection errors and completely block your application from functioning during production deployments. This CLI command finalizes the permission grant within your directory policy. You specify the target application identifier and explicitly define the consent scope for administrative approval. Executing this properly ensures the application holds valid authorization to access protected APIs on behalf of users without triggering compliance alerts or audit failures. Remember this core principle as you architect complex cloud solutions. Identity functions as the modern security perimeter rather than a simple login feature. Every provisioned resource must be protected by conditional access policies and least privilege controls to prevent lateral movement attacks and maintain strict regulatory compliance across your entire environment. Let's verify your comprehension of these core directory concepts. Which specific identity object represents an application instance within a tenant and enables secure resource access? Is it the user account, the tenant boundary, or the service principal? Understanding this distinction is essential for passing the certification exam and configuring correct RBAC assignments in production. For hybrid environments, you must strategically select an identity synchronization method. Password hash synchronization is the simplest approach, continuously syncing hashed credentials to the cloud for immediate availability. Pass-through authentication validates logins against on-premises Active Directory in real time without storing passwords in Azure. Federation leverages ADFS for custom single sign-on policies, but increases infrastructure complexity significantly. We have thoroughly covered the essential components of Microsoft Entra ID architecture. You mastered tenants as your security foundation and learned how service principals enable secure automation. We compared authentication methods and practiced registering applications with precise CLI parameters. Finally, we evaluated hybrid identity strategies to safely bridge on-premises directories with cloud workloads. For the AZ-305 exam, focus heavily on distinguishing between Azure, RBAC assignments, and Entra ID built-in roles. Memorize when to deploy managed identities versus legacy service principals for automation workloads. Understand the architectural trade-offs between password hash synchronization and pass-through authentication for hybrid designs. Practice interpreting CLI commands to avoid common permission misconfiguration traps. Imagine handing out physical keys to every contractor who visits your office. Managing those keys manually quickly becomes a security nightmare and an administrative burden. Designing identity solutions for B2B collaboration solves this by establishing digital trust relationships that let partners access exactly what they need using their own corporate credentials, eliminating password fatigue and centralizing control for IT teams. Configure Azure AD B2B with conditional access policies targeting specific resource groups. Skip this architecture, and you risk credential sprawl and compliance violations during an audit. We will start by exploring guest user workflows and invitation mechanics. Next, we will examine direct connect features for Teams shared channels. Then we will cover cross-tenant synchronization for multi-tenant organizations. Finally, we will review application integration patterns and security hardening strategies. You will use the Azure CLI command as REST to automate these setups during lab exercises. Understanding these workflows matters because misconfigured guest policies can expose your entire tenant to unauthorized data access. Review each step carefully to pass the certification exam confidently. Before we dive into the mechanics, we need to understand federation. This is simply establishing a trust relationship between two identity providers. Instead of managing separate passwords for every partner, your directory trusts the authentication performed by their corporate system. For instance, configure Azure AD-SAM LSSO endpoints to validate signatures from Okta or Ping Federate. This matters because broken trust chains cause immediate login failures across all integrated applications. Verify metadata URLs carefully to prevent authentication bypasses during peak traffic hours. Architect secure external access patterns using this concept regularly. First, send an invitation to the external email address through your internal portal or automated workflow. This triggers a verification check against your directory policies and prepares the guest record for creation. The system validates that the target domain is allowed and flags any restricted users before proceeding. Use the Microsoft Graph API endpoint invitations with the message property set to true. This matters because missing domain restrictions allows unverified contractors to access sensitive workspaces. Always test invitations in a sandbox tenant before deploying to production. We use the Microsoft Graph API to automate this invitation process. The request targets the invitation's endpoint with the partner's email address and a redirect URL for after they sign in. Setting the message flag to true triggers Azure AD to send the redemption link directly to their inbox, streamlining the onboarding experience. Execute commands like as-rest method, post URL invitations with JSON payloads containing the requested email address field. This matters because automated provisioning reduces manual errors that frequently cause access delays. Always validate redirect URIs against your approved domains. Next, the external user accepts the invitation and authenticates directly at their home identity provider. This step verifies their credentials against their corporate system without exposing your directory to direct login attempts. The authentication result is packaged into a secure token that travels back to your environment. Monitor this flow using Azure Monitor logs with query filters for activity category equals authentication. This matters because improper token validation exposes session cookies to man-in-the-middle attacks. Enforce short-lived token expiration policies to limit credential compromise impacts. Now let's look at how data flows when you use B2B Direct Connect for Teams. The partner authenticates directly at their home identity provider. Azure AD validates the token through a bilateral tenant trust, and the shared channel grants access immediately without creating a guest account in your directory. Configure this feature using the Microsoft Teams PowerShell module, command new CS online application access policy to whitelist specific external domains. This matters because bypassing guest provisioning reduces administrative overhead, but requires strict network segmentation. Trust boundary misconfigurations risk exposing internal Teams channels to unauthorized viewers. Finally, assign resources and enforce conditional access policies to lock down the environment. This step ensures that only approved applications and data sets are exposed to the guest identity. Continuous monitoring verifies that access remains aligned with business requirements. Implement these controls using Azure CLI commands like as-add-app update to restrict permitted URIs and set explicit grant types. This matters because overly permissive policies allow guests to escalate privileges beyond their intended scope. Always review policy assignments quarterly to remove stale permissions before they trigger security audits. Choosing the right mechanism depends on your collaboration depth. Guest users are ideal for ad hoc project access and create a directory object. Direct Connect eliminates guest accounts entirely, making it perfect for deep Teams collaboration. Cross-tenant sync automates provisioning across multiple tenants for large multi-tenant organizations. Evaluate these options using the Azure AD Identity Governance portal to compare licensing tiers and sync interval settings. This matters because selecting the wrong model increases management costs and complicates compliance reporting. Document your architecture to ensure consistent policy enforcement across environments. Once collaboration is established, you must harden the environment. First, enforce multi-factor authentication through conditional access policies for all external identities. Next, apply least privilege controls so partners only see what they strictly need. Finally, monitor guest activity continuously using audit logs to detect anomalies early. Configure these safeguards using as-add policy, create with explicit session timeout values set to 30 minutes. This matters because weak baseline configurations leave your tenant vulnerable to credential stuffing attacks. Test policies in report-only mode before enabling enforcement to prevent user lockouts. Remember this core principle for your design decisions. Trust between directories is established once during federation setup, but access to resources must be verified continuously through conditional policies and monitoring. This mindset prevents privilege creep and keeps your external collaboration secure across all projects. Implement this approach using Azure AD Conditional Access with dynamic device filters and explicit IP range restrictions. This matters because static trust models fail when external networks change frequently. Validate session tokens against risk signals to maintain compliance during scaling events. Let's pause to check your understanding. Which B2B feature eliminates guest account creation in the target tenant? The correct answer is B2B Direct Connect, which relies on a bilateral tenant trust to grant access without provisioning directory objects. This distinction frequently appears on certification exams, so review it carefully. You will encounter this concept when configuring as graph query to filter results for object class equals user versus device identities. Understanding this difference matters because misidentifying the architecture leads to incorrect licensing calculations and failed audit responses. When integrating applications, multi-tenant apps accept sign-ins from any Azure AD tenant and prompt for user consent. Single-tenant applications require explicit guest invitations to function. Designing for external access increases your attack surface by roughly 40% if you do not implement strict conditional access rules. Configure these boundaries using as-add-sb create for RBAC with explicit application IDs and controlled redirect URIs. This matters because uncontrolled consent flows grant excessive permissions that bypass traditional network perimeters. Always restrict tenant-wide admin consent to senior architects to prevent accidental privilege escalation across shared workloads. We covered the core B2B mechanisms. Guest users provide flexible ad hoc access through invitations. Direct Connect streamlines Teams collaboration by removing guest provisioning. Cross-tenant sync automates multi-tenant management for large enterprises. Hardening always requires MFI and least privilege controls. Implement these patterns using as-REST endpoints with explicit timeout parameters set to 90 seconds. This matters because inconsistent configuration standards create deployment bottlenecks that delay critical project milestones. Always document your architectural choices to ensure repeatable and auditable infrastructure deployments across all teams. For the AZ-305 exam, focus on knowing when to use direct connect versus guest users based on collaboration depth. Understand multi-tenant application consent flows and how they differ from single-tenant setups. Always apply conditional access policies to external identities and recognize the specific limitations of cross-tenant synchronization. Practice these scenarios using as-add-user, create with explicit account-enabled flags set to false for test accounts. This matters because exam questions frequently test your ability to distinguish between authentication methods and authorization boundaries. Master these distinctions to confidently pass the certification assessment early. Imagine running a massive concert venue without ticket scanners or security gates. Chaos would ensue within minutes. B2C identity solutions act as those digital checkpoints, managing millions of consumer accounts securely while keeping login friction low. In this lesson, we will explore customer-facing identity requirements, dive into Azure AD B2C user flows, and integrate MSAL to build a production-ready sign-in system. Skipping proper configuration risks severe account takeover vulnerabilities during peak traffic spikes. We begin by defining the core characteristics that distinguish consumer identity from traditional employee directories. Next, we examine scalability and compliance requirements for handling millions of external accounts. Then, we design a secure B2C user flow using Azure AD B2C policies to standardize sign-in steps. Finally, we integrate MSAL into your front-end code to handle token exchanges seamlessly, preventing session hijacking during high-volume traffic windows. B2C identity focuses on managing external consumer accounts for applications like e-commerce or streaming platforms. Unlike internal employee directories, these systems must handle millions of diverse users with varying technical skills. The priority shifts heavily towards self-service password resets and seamless social logins via OAuth 2. A robust architecture targets 99.9% availability to prevent checkout abandonment during global peak traffic spikes. The authentication process follows a strict sequence to ensure security and performance across distributed systems. First, the user requests access to your protected endpoint. Next, MSAL redirects the browser to the Azure AD B2C tenant for verification. Once authenticated, the service returns a signed ID token to the client. Finally, the application validates the signature and grants secure access to the requested resources, preventing unauthorized data exposure. In Azure AD B2C, a user flow serves as the core mechanism for defining the customer experience. It acts as a pre-configured policy that dictates exactly how users sign up, sign in, or edit their profiles without custom code. You define available identity providers and collected attributes to ensure a consistent journey. Misconfiguring these flows directly impacts conversion rates and violates GDP, our data minimization principles. When designing identity solutions, you must clearly distinguish between business-to-employee and business-to-consumer scenarios. B2E relies on enterprise SSO and admin-managed profiles for thousands of internal staff. In contrast, B2C demands social logins and self-service management for millions of external users. Failing to separate these architectures exposes sensitive customer data to compliance audits and violates strict GDP, R and CCPA regulatory boundaries. First, we select the identity providers and local accounts that consumers can use to access the application securely. This foundational step determines whether users sign in with social credentials like Microsoft or create a local account directly within your directory. You must evaluate which options align with your target audience. Selecting the wrong providers increases authentication latency and reduces overall platform adoption rates. This JSON configuration defines the available identity providers for your user flow. You specify the Facebook client credentials for social login and add a local account type to allow users to create standard email and password accounts directly in your directory. This setup ensures flexibility for diverse consumer preferences. Incorrectly mapping these scopes will trigger immediate authentication failures during production deployment. Next, we enforce multi-factor authentication and strict password policies to secure the user accounts effectively. This step ensures that consumers use strong credentials and verify their identity through SMS or authenticator apps during sensitive operations. Implementing these controls reduces the risk of account takeover and protects sensitive customer data from unauthorized access. Skipping MFI enforcement exposes your platform to credential stuffing attacks. This configuration enforces a password policy requiring complexity and expiration, while mandating SMS-based multi-factor authentication for every sign-in. It also defines the custom attributes collected during the sign-up process to enrich the user profile with essential details. You can apply these settings using the AZ-add B2C user flow update command to enforce compliance across all tenant regions. Finally, we integrate the MSAL library into your application to handle the authentication flow seamlessly. This step connects your front-end code to the Azure AD B2C tenant, managing tokens and ensuring users are authenticated before accessing protected resources. Proper integration ensures that security policies are enforced consistently across all user interactions. Neglecting token caching will cause excessive network calls and degrade mobile performance. This MSAL configuration connects your application to the B2C tenant using the specific authority URL, which includes your tenant name and user flow policy. It sets the client ID for authentication and configures session storage to securely manage tokens during the user browsing session. You must verify the login endpoint matches your exact region to prevent routing delays. Remember this principle: security must never compromise usability, because a secure identity system is useless if customers abandon the sign-in process. The goal is to balance robust protection with frictionless access for every consumer. Always prioritize user experience while maintaining strict security controls to drive adoption and retention. Overcomplicating verification steps directly increases your application bounce rate by over 30%. Let's test your knowledge. Which Azure AD B2C component dictates the specific steps and attributes collected during user sign-up? The correct answer is a user flow policy, which defines the entire customer journey from sign-in to profile management. Understanding this policy structure is essential for designing flexible and secure identity solutions. Misconfiguring it will break downstream IPI authorization checks completely. To recap, B2C identity solutions prioritize user experience and massive scalability. Using managed services like Azure AD B2C, you must enforce strict MFI and compliance standards while integrating MSAL to handle secure authentication flows in your applications. Focus on self-service capabilities and robust security measures to ensure a successful customer-facing identity strategy. Neglecting these controls will trigger immediate audit failures during certification reviews. For the AZ-305 exam, focus on the differences between B2E and B2C scenarios. You should be able to configure user flows, understand MSAL authority URLs, and prioritize GDP are compliance when designing identity solutions for customer-facing applications. Practice identifying the correct authentication protocols and security policies required for specific business-to-consumer requirements. Missing these details will cost you critical points on scenario-based questions. Picture walking through a high-security airport terminal where every passenger faces a multi-layer screening process before boarding. Conditional access operates exactly like this rigorous checkpoint inside Microsoft Entra ID. It inspects each sign-in request against dynamic rules regarding device compliance, geographic location, and risk level before granting or denying entry. You must configure these policies carefully because misconfigured rules can lock out legitimate users or leave sensitive tenant data exposed to unauthorized access attempts. We will master conditional access policy design by breaking down assignments, conditions, and grant controls into manageable steps. You will learn to target specific Entra ID groups like cloud admins while excluding service principals. We will examine how risk signals trigger step-up authentication and why evaluation order prevents accidental lockouts. Finally, we will configure policies using the AZ-CLI command set and understand exact licensing tiers required for your certification exam. Conditional access functions as the primary enforcement engine inside Microsoft Entra ID P2. It evaluates every sign-in request against configurable conditions, including device platform, location, and risk level. When those conditions align, the system immediately applies grant controls, such as requiring multi-factor authentication or blocking access entirely. You must validate these rules thoroughly, because an incorrectly configured rule can halt business operations across your entire organization. We begin designing a policy by strictly defining the assignments section. You must explicitly include target groups like global administrators while carefully excluding emergency break glass accounts. This precise scoping prevents accidental lockouts during critical incidents. If you forget to exclude privileged service accounts, your entire tenant could become inaccessible until you manually restore access through an alternate authentication method. Consider enforcing multi-factor authentication for all directory administrators. You will navigate to the Include section and select the directory roles property, specifically checking Global Administrator and Security Administrator. Then you must add your emergency break glass accounts to the exclude list immediately. Failing to exclude these critical accounts will permanently lock out your own team during a tenant migration or password reset operation. Next, you will configure the Conditions section to establish precise evaluation criteria. You can filter requests based on specific device platforms like iOS or Android, geographic locations, such as restricted countries, and client applications targeting mobile apps. Understanding these parameters is essential because misconfigured filters will either force unnecessary authentication prompts or leave critical endpoints completely unprotected from unauthorized access attempts. Consider requiring a fully compliant device for accessing Salesforce through Entra ID. You will select Device State under Conditions and specify that devices must report a status of compliant or hybrid Azure AD joined. This ensures only managed endpoints can reach sensitive applications. If you skip this validation, unpatched personal devices could expose corporate data to malware or unauthorized network sniffing attacks. Finally, you will configure the Grant Controls section to define the actual enforcement action. You can select block access for immediate denial or require multi-factor authentication for step-up verification. You should also enable session controls like limiting sign-in frequency to 90 minutes. Ignoring these session parameters allows attackers to maintain persistent access tokens long after a legitimate user has logged off. You will manage these configurations directly through the Microsoft Graph API using standard REST endpoints. Run a GET request against the Identity Conditional Access Policies endpoint to retrieve every active policy in your tenant. This automated approach allows you to audit display names and enabled states efficiently. Without programmatic auditing, you risk deploying conflicting rules that silently override your intended security posture. Let us compare the primary grant controls available in the portal. Block access immediately terminates the authentication flow without generating tokens. Require multi-factor authentication forces a secondary verification step before granting entry. Require device state validates in-tune compliance records first. You can combine these using all or one of logic, but selecting all will strictly enforce every single requirement simultaneously. Understanding the sequential evaluation logic is absolutely critical for passing the certification exam. The system processes every applicable policy from top to bottom in your tenant configuration. If multiple policies apply simultaneously, the most restrictive outcome always wins. A block access rule will permanently override any grant rule, which means misordered policies will unexpectedly lock out legitimate administrators during peak hours. Quick check question for your exam preparation. You have two active policies applying to the same user account. Policy A requires multi-factor authentication, while Policy B blocks access from a specific IP range. The user attempts to sign in from that restricted IP address. The system will immediately deny the request because the block rule takes precedence over the MFI requirement. Licensing requirements represent a frequent exam topic that you must memorize precisely. Basic conditional access functionality requires either Entra ID P1 or P2 subscriptions. However, advanced risk-based features like user risk and sign-in risk detection strictly require the P2 tier. Always verify your subscription level before deploying risk policies, because attempting to enable these controls on a P1 license will generate immediate configuration errors. A critical certification term to master is the break glass account concept. This dedicated emergency access identity must be explicitly excluded from every single conditional access policy in your tenant. It ensures administrators can always authenticate even when misconfigured rules lock out the entire organization. Failing to isolate these credentials will trap your security team during a critical incident requiring immediate tenant recovery. Let us compare the exact licensing feature grid for your exam preparation. The P1 tier includes basic conditional access functionality and named location tracking. The P2 tier adds advanced risk-based policies and direct integration with identity protection. Higher enterprise tiers introduce detailed audit reporting. You must match these specific features to your organizational requirements, because requesting P2 capabilities on a P1 license will fail validation. Remember this fundamental security principle for your certification exam: never trust, always verify. Conditional access serves as the primary enforcement engine that transforms this abstract concept into measurable reality. The system actively verifies every single access attempt against dynamic risk signals and device compliance records before issuing authentication tokens. Ignoring these verification steps will leave your cloud infrastructure vulnerable to credential theft attacks. We have covered the essential components required for your conditional access certification exam. You learn to design policies using precise assignments, dynamic conditions, and strict grant controls. We reviewed specific grant mechanisms like MFI verification and in-tune compliant device validation. You mastered the evaluation logic, where the most restrictive rule always wins. Understanding these exact parameters prevents accidental tenant lockouts during production deployments. For the AZ-305 exam, focus heavily on policy evaluation logic and licensing distinctions. Exam questions will frequently present overlapping policies and ask you to determine the final access outcome. Remember that the most restrictive rule always wins during sequential processing. You must also know that break glass accounts require explicit exclusion from every policy. Distinguishing between P1 and P2 risk features will directly impact your score. Imagine securing a high-value vault with two completely different keys. One key is something you know, like a combination code. The second key is something you physically hold, like a metal token. Even if an attacker steals the combination, they cannot open the vault without the physical key. This is exactly how multi-factor authentication protects your digital assets. In this lesson, we will explore why MFI is non-negotiable for modern security, compare the available methods, and design a robust strategy tailored to your organization's risk profile using Azure Conditional Access policies. We begin with the core fundamentals and the three distinct factors that make authentication work reliably. Next, we compare implementation methods, weighing their cryptographic strength against daily user experience. Then, we move into a hands-on design process for selecting the right strategy for your Azure environment. Finally, we examine integration patterns and how verification flows through Entra ID. Mastering this sequence prevents misconfigured policies that lock out legitimate administrators during critical deployments. Multi-factor authentication is a security mechanism that requires users to present two or more distinct verification factors to gain access. These factors must come from different categories: something you know, something you have, or something you are. This requirement ensures that compromising a single factor, like a password, is not enough to breach an account. For the AZ-305 exam, you must recognize that combining knowledge with possession blocks credential stuffing attacks, targeting legacy, on-premises directories, and cloud workloads alike. Knowledge factors are information only the user should know, such as passwords or PINs. Possession factors involve a physical item the user holds, like a smartphone receiving a code or a hardware security key. Inherence factors rely on unique biological attributes, such as fingerprints or facial scans. Using factors from different categories ensures that if one is compromised, the attacker still cannot authenticate. Misconfiguring these categories can lead to weak single-factor fallbacks that bypass enterprise security controls entirely. SMS OTP is widely adopted but vulnerable to SIM swapping and phishing. Authenticator apps generate codes offline and are more secure, though users can still be tricked into entering them. Push notifications offer a better user experience with one-tap approval, but MFI fatigue attacks can lead to accidental approvals. Security keys provide the highest security with phishing resistance, while biometrics offer convenience and strong cryptographic backing. Choosing the wrong method exposes your tenant to automated credential harvesting tools. We follow a sequential process to ensure security without sacrificing usability. First, assess the risk profile of your resources and users. Second, select appropriate methods based on that risk. Third, enforce policies using conditional access to automate the experience. For example, applying strict MFI to administrative groups prevents lateral movement during breach scenarios. Skipping this step leaves critical workloads exposed to unverified access attempts that compromise sensitive data stores. This configuration enforces MFI for all users accessing the finance application from untrusted networks. It defines the conditions for access and specifies the authentication strength required, ensuring that high-risk scenarios trigger the appropriate challenge. You would implement this using the Azure CLI command as add app update to assign the required policy ID. Failing to scope these rules correctly can accidentally block emergency break glass accounts during active incidents. Once risk is assessed, we select methods that balance security and usability. For administrators, we choose phishing-resistant keys. For general users, we might opt for push notifications or authenticator apps. This tiered approach ensures that privileged roles like global administrators face stricter verification thresholds. Ignoring this distinction forces you to deploy overly complex workflows that degrade daily productivity across your engineering teams. These policies automate the MFI challenge based on context such as user role, location, and device compliance. This ensures that high-risk scenarios always trigger stronger authentication without manual intervention. You can configure specific rules in Entra ID to block access from non-compliant devices or unfamiliar IP ranges. Neglecting these automated checks allows attackers to exploit weak endpoints and bypass your perimeter defenses entirely. You should always offer multiple MFI options where possible, allowing users to choose the method that best suits their workflow while still meeting security policies. Mandate strong methods for privileged access, but provide flexibility for general users to reduce friction and support adoption. For instance, permitting both FIDO2 keys and Microsoft Authenticator balances compliance with daily efficiency. Rigid single-method mandates inevitably increase help desk ticket volume during credential rotation cycles. Which MFI method provides the highest resistance to phishing attacks? Is it SMS, OTP, authenticator apps, push notifications, or security keys? Think about how each method verifies the origin of the request. The correct answer is security keys because they use cryptographic binding that invalidates stolen credentials entirely. Understanding this distinction prevents you from selecting weak verification methods that fail during active social engineering campaigns targeting your organization. The user initiates login with credentials to the application. The app redirects to the IDP, which evaluates the risk and challenges the user for MFI. The user provides the second factor, such as a code or biometric scan. The IDP validates this and issues a token back to the application, granting access. This SAM-L or OIDC flow ensures that token validation occurs server-side rather than client-side. Breaking this chain exposes your IPIs to unauthorized session hijacking attempts. MFI is typically managed by an identity provider, which centralizes authentication and handles the entire flow. Alternatively, you can implement application-level MFI directly in the code, though this is discouraged due to complexity and maintenance overhead. Centralizing verification through Entra ID PIM reduces redundant development effort across multiple microservices. Building custom logic inevitably introduces synchronization errors that delay critical access approvals during peak operational hours. The server returns a status indicating MFI is required, along with a challenge ID and available methods. The client must then prompt the user to complete the challenge using one of these methods before proceeding. A typical HTTP 401 response includes a www authenticate header specifying bearer scheme requirements and token lifetime parameters. Failing to parse these headers correctly causes authentication loops that disrupt automated deployment pipelines and block service account operations. MFI requires two or more distinct factors to prevent unauthorized access. You must compare methods like SMS, apps, push, and keys based on security and usability. Design your strategy by assessing risk, selecting methods, and enforcing policies via conditional access. Finally, use an identity provider for centralized management rather than building custom logic. Mastering these steps ensures your architecture passes AZ-305 design scenarios while maintaining strict compliance with enterprise audit standards. You will be asked to select the appropriate method for different user groups and resources. Remember that security keys are phishing resistant and should be mandated for privileged accounts. Conditional access is your primary tool for enforcing MFI policies based on context. Understand the flow of authentication through an IDP and the trade-offs between SMS, apps, and hardware keys. Practicing these scenarios with real CLI commands builds the muscle memory needed to ace the performance-based exam questions. Imagine checking into a hotel where every room has its own unique keycard that automatically expires the moment you check out. There are no lost keys to worry about, and perfect security for every guest. That is exactly how managed identities transform authentication in Azure, removing the burden of secret management entirely. For your AZ-305 exam, this feature eliminates hard-coded connection strings across app service and virtual machines. If you skip this configuration, developers accidentally commit secrets to GitHub, triggering immediate compliance violations and costly security incidents. In this lesson, we will explore what a managed identity is and how it simplifies authentication. We will compare system-assigned versus user-assigned types to help you choose the right model. Then we will walk through the implementation workflow for granting access, and finally look at code integration patterns using default Azure credential. Mastering these distinctions directly impacts your AZ-305 score, since exam questions frequently test resource linkage scenarios. If you misconfigure the assignment scope, applications fail to retrieve secrets, causing immediate service outages during peak traffic windows. A managed identity is an automatically managed identity in Azure Active Directory for a resource. When you enable it, Azure creates a service principal behind the scenes that can authenticate to any service supporting Azure AD authentication. You never handle the credentials. Azure manages the lifecycle and rotation completely. This architecture directly satisfies compliance requirements for zero-trust environments. If you manually rotate secrets instead of enabling this feature, your automation scripts break overnight, halting critical deployment pipelines and triggering audit failures during quarterly reviews. When you enable a managed identity, Azure provisions a service principal tied to that resource. This principal obtains OAuth2 access tokens automatically when your code requests them. The magic lies in the automation. Credentials are rotated with 100% reliability by the platform, eliminating human error and reducing security risks significantly. Exam scenarios frequently test this token acquisition flow against services like Azure Key Vault or Cosmos DB. If you bypass this automated rotation, expired certificates immediately block IPI calls, causing cascading failures across dependent microservices. You have two choices for managed identities. System-assigned identities are tied directly to the resource lifecycle. If you delete the resource, the identity vanishes. User-assigned identities are standalone resources that can be shared across multiple services and managed independently. Choose system-assigned for simple scenarios and user-assigned when sharing is required. The AZ-305 exam heavily tests this distinction during architecture design questions. If you incorrectly bind a user-assigned identity to a single app service plan, you waste management overhead and complicate permission audits unnecessarily. Let's implement access for a managed identity step by step. First, we enable the identity on the target resource. Next, we assign an RBAC role to that identity to grant permissions. Finally, we configure the application code to use the credential automatically. We will build this cumulatively as we progress through each phase. This structured approach prevents permission drift across complex cloud environments. If you skip the explicit role assignment step, your applications receive 0 access tokens, resulting in immediate HTTP 403 forbidden errors during runtime execution. Here is how we enable a system-assigned identity on a function app using the Azure CLI. The command creates the resource group and storage account, then provisions the function app with the assign identity flag. This single flag triggers the creation of the service principal and links it to the app automatically. You must verify the output contains the principal-id property before proceeding. If you omit this flag during deployment, the platform cannot generate valid OAuth tokens, causing immediate authentication failures against downstream databases. Now we expand the workflow. We have enabled the identity, and now we must assign an RBAC role to grant specific permissions. This step authorizes the identity to access other resources securely without exposing secrets. The assignment must target the exact resource ID where the protected data resides. If you apply broad contributor roles instead of granular reader permissions, you violate least privilege standards and increase your attack surface during potential breach investigations. To assign the role, we first retrieve the principal ID of the managed identity. Then, we create a role assignment linking that ID to the key vault with the key vault secret user role. This grants the function app permission to read secrets without storing any connection strings. You should always verify the assignment scope matches the exact subscription or resource group boundary. If you misconfigure the target scope, the platform denies token requests silently, forcing developers to waste hours debugging apparent code defects. Finally, we complete the workflow by configuring the application code. The code uses default Azure credential to automatically detect the managed identity and obtain tokens. This ensures the application authenticates seamlessly without hardcoding any secrets. You must ensure the runtime environment variables match the expected Azure Cloud endpoint configuration. If you point the credential object to an on-premises directory instead of the tenant context, the authentication pipeline fails immediately, blocking all downstream data retrieval operations. This C# snippet demonstrates the code integration. We use default Azure credential to authenticate against Key Vault. The SDK automatically detects the managed identity context and fetches the secret. No credentials are stored in the environment variables or code. You should always wrap this call inside a standard try-catch block to handle transient network timeouts gracefully. If you ignore exception handling, brief latency spikes during token acquisition will crash your entire request processing loop unexpectedly. Quick check: which managed identity type allows you to share the same identity across multiple Azure resources, such as a cluster of VMs? Is it system-assigned or user-assigned? The correct answer is user-assigned because those identities exist independently within your subscription and can be attached to any compatible compute service. Understanding this distinction prevents architectural missteps during exam scenario questions. If you confuse the two models, you will incorrectly design tightly coupled deployments that become impossible to scale or troubleshoot later. Always follow the principle of least privilege when assigning roles to managed identities. Grant only the minimum permissions necessary to perform the task, avoiding broad roles like contributor unless absolutely required. This approach directly reduces your organization's blast radius during potential security incidents. If you assign owner permissions to a routine data processing identity, attackers could pivot through your entire subscription and modify critical billing configurations without detection. we covered the core concepts of managed identities. You learned how they automate authentication via Azure AD, compared system-assigned versus user-assigned types for different scenarios, and walked through the implementation workflow from enabling identity to assigning roles and integrating code. Mastering these patterns directly prepares you for performance-based exam questions requiring precise architectural decisions. If you overlook the RBAC assignment step during lab exercises, your final deployment will fail validation checks and cost you valuable certification points. For the AZ-305 exam, focus on distinguishing between system and user-assigned identities in scenario questions. Know how to assign RBAC roles to managed identities using CLI or Portal. Understand that default Azure credential handles authentication automatically in Azure environments without manual secret configuration. You should practice writing exact command syntax under timed conditions to build muscle memory for the actual test environment. If you rely on memorized conceptual descriptions instead of precise parameter knowledge, you will lose points on detailed implementation questions. Imagine you are designing a secure office building. That blueprint defining doors and access points is exactly an app registration in Azure AD. But to actually open those doors, you need a physical keycard issued for that specific structure, which represents your service principal. In this lesson, we will explore how these two identities work together to secure cloud applications and automate access to Azure resources safely. We will start by defining the core concepts of app registrations and service principals. Next, we will examine how they interact in single-tenant versus multi-tenant directories. Then we will execute a hands-on setup using the as-add-sb create for RBAC command. Finally, we will cover managed identities and review critical AZ-305 exam tips to prevent authentication failures during your certification test. Let us start with the foundation. An app registration is the global definition of your application within the Microsoft Identity Platform. When you register an app, you specify supported account types and define exactly which Microsoft Graph APIs it can access. This registration persists globally until you deploy it into a specific directory, where failing to configure redirect URIs will immediately block OAuth flows. When you create an app registration, you configure several key components that dictate application behavior. You set supported account types to single-tenant or multi-tenant options and define redirect URIs for web flows. You also configure API permissions and manage credentials like client secrets or certificates. Misconfiguring these settings will cause immediate token validation errors during production authentication. Understanding the relationship between these objects is critical for troubleshooting access issues. An app registration acts as the blueprint, while the service principal is the tenant-specific instance created when you use that app in a directory. In single-tenant scenarios, both exist together. For multi-tenant apps, the registration stays home while a service principal auto-creates in every consenting tenant, preventing unauthorized resource access. Let us walk through setting up a service principal for automation. First, create the app registration to define the identity and capture its application ID. Next, generate a service principal object in your target tenant and retrieve a client secret. Finally, assign an Azure RBAC role at the appropriate scope to grant access. Skipping this step will lock your deployment scripts from reaching storage accounts. Here is how you implement that setup using the Azure CLI. We start by creating the app registration and capturing its application ID. Then we create the service principal linked to that app ID, which generates a client secret automatically. Finally, we run as role assignment create to grant the contributor role on our target resource group, preventing permission denied errors during automated deployments. Now that we have the identity created, we must ensure it holds exactly the right permissions. The service principal acts as the security context for the application within the tenant. When you assign an RBAC role, you grant the ability to perform actions on specific Azure resources. Scoping these permissions incorrectly will trigger excessive access warnings and violate compliance auditing standards. This code snippet demonstrates how to grant permissions securely. We define the target resource group and the desired role name. By running the role assignment command with the application ID as the assignee, Azure AD resolves this to the service principal and applies the role at the resource group scope. This ensures automation scripts manage resources without storing user credentials in plain text. Finally, we verify the setup and enforce security best practices. Once the service principal is created and role assigned, you can use the credentials to request tokens from Azure AD. The application uses these tokens to authenticate against IPIs or manage resources. Always review assigned roles to ensure they match the principle of least privilege for your specific automation task. It is helpful to compare these objects side by side to avoid confusion during exams and real-world scenarios. The app registration is the global definition that exists across all tenants, while the service principal is the tenant-specific instance used for authentication. You assign IPI permissions at the registration level, but you assign RBAC roles to the service principal within a specific directory. For applications hosted directly within Azure, you must know about managed identities. A managed identity is a special service principal automatically created and managed by the platform for resources like virtual machines or app services. It eliminates storing credentials in your code because Azure handles token acquisition automatically on your behalf, preventing secret leakage during routine maintenance cycles. To secure your identities effectively, follow these proven practices. Always use certificates instead of client secrets for production environments to reduce leakage risk. Store necessary secrets in Azure Key Vault rather than hard-coding them. Regularly rotate credentials and monitor sign-in activity to detect anomalies. Prefer managed identities whenever possible to simplify authentication and reduce administrative overhead during scale events. Keep this principle in mind as you design your solutions. Security is not just about access. It is about the minimum necessary access required to perform a task. By adhering to least privilege and automating identity management, you build resilient systems that are easier to audit and harder to compromise. Failing to enforce this will trigger compliance violations during security reviews. Let us test your understanding of the relationship between these objects. If you register a multi-tenant application in your home tenant, where does the service principal object exist for users from other organizations? Is it in the home tenant, the user tenant, or both? Think about how consent works across directories before checking the answer, as misplacing this will cause authentication routing failures. We have covered the essential aspects of application identities in Azure. You learned that app registrations serve as global blueprints, while service principals act as tenant-specific instances for authentication. You practiced provisioning identities using the CLI and assigning RBAC roles securely. Finally, we emphasized managed identities and least privilege to keep your environment safe from unauthorized access attempts. For the AZ-305 exam, focus on distinguishing between app registrations and service principals in scenario-based questions. You will likely be asked to identify where permissions are assigned or how to troubleshoot authentication failures. Remember that IPI permissions go to the registration, while RBAC roles go to the service principal. Also, recognize when managed identities are recommended for Azure-hosted workloads. Imagine you are managing a large hotel. You could hand every guest a master key that opens every door, but that would be a security nightmare. Instead, you issue specific room keys based on who booked which suite and what services they paid for. Access control works the same way in it. We must ensure users only access exactly what they need, no more and no less. In this lesson, we will design robust RBAC systems using Azure CLI commands to prevent privilege escalation and meet exam objectives. We will start by breaking down the core components and how they interact across Azure management groups and subscription scopes. Then we will dive into the procedural steps of designing a secure model, which is critical for your AZ-305 exam. After that, we will compare different RBAC variants to know when to use them. Finally, we will cover security best practices and key takeaways for the certification. Skipping these steps often leads to misconfigured permissions and costly compliance failures during audits. Role-based access control is a method of regulating access to resources based on the roles assigned to individual users within an organization. Instead of granting permissions directly to every user, you assign permissions to predefined roles like reader or contributor, and then assign users to those roles. This abstraction simplifies management and enforces security policies consistently. Failing to use this model typically results in permission sprawl and makes it nearly impossible to revoke access during a security incident. At the heart of any RBAC system are 4 core components. Users represent the people or managed identities requiring access. Roles act as containers for specific job functions stored in Azure AD. Permissions define the actual actions allowed on resources through action strings. Finally, resources are the assets being protected at specific scopes. Understanding these elements and their relationships prevents accidental overprovisioning when you configure access across multiple subscriptions. Visualizing the flow helps clarify the relationships. Users are assigned to roles, which can be many-to-many across different management groups. Roles hold permissions, also a many-to-many relationship defined by JSON action arrays. Permissions grant access to specific resources at the subscription or resource group level. This layered approach ensures that if a user changes jobs, you only update their role assignment, not every individual permission they held before. Now let's look at the procedure for designing an RBAC model. We will walk through this step by step to ensure you can implement it correctly. First, we define the roles and permissions based on business requirements using a structured JSON file. You must specify exact actions and data actions to prevent scope creep. Skipping this documentation phase often leads to misconfigured custom roles that fail security audits during certification exams. Here is a practical example of defining roles and permissions in a database schema. This SQL snippet creates the core tables for users, roles, and permissions. It also establishes junction tables to manage the many-to-many relationships between them. Notice how the foreign keys enforce referential integrity across the structure. Applying this same logic in Azure requires precise JSON formatting to avoid deployment failures when you run as role definition create. Moving to the second step of our design process. Once roles and permissions are defined, we must map users to those roles using specific scope IDs. This step ensures that every user has the appropriate access level for their specific responsibilities within the organization. You should always assign roles at the most granular scope possible to prevent accidental elevation. Misplaced role assignments frequently cause unauthorized resource modifications during production deployments. This code demonstrates the authorization logic for checking user permissions. The function retrieves the user's roles and then checks if any of those roles contain the required permission. This pseudocode illustrates how an application enforces access control at runtime by validating against the defined role permission mappings. Always pair this logic with Azure AD Conditional Access policies to block unauthorized IPI calls before they reach your resources. Finally, we enforce the principle of least privilege throughout the design. This means assigning only the minimum permissions necessary for a user to perform their job. We must also regularly audit and review these assignments to prevent permission creep over time. You should avoid granting the owner role unless absolutely required. Overprivileged accounts dramatically increase your attack surface and frequently trigger compliance violations during certification assessments. Here is a JSON configuration snippet representing a role assignment in a modern system. It shows how a user is linked to a specific role with an expiration date for temporary access. This structure supports audit trails and ensures that access is time-bound where appropriate, reducing long-term risk. Always configure automatic expiration using the expires parameter in your CLI commands. Forgetting this setting leaves dormant credentials vulnerable to credential theft attacks. It is important to understand the different RBAC models available. Flat RBAC is simple and independent, suitable for small teams managing single subscriptions. Hierarchical RBAC introduces inheritance, allowing roles to gain permissions from parent roles across management groups. Constrained RBAC adds rules like separation of duties to prevent conflicts, which is essential for regulated industries. Choosing the wrong model often causes permission overlap and makes troubleshooting access failures extremely difficult during exams. Remember this key principle for your design work. Always apply the principle of least privilege. Users should only have the access they need to perform their duties, nothing more. This minimizes the blast radius of compromised accounts and simplifies compliance auditing. You must restrict custom roles to specific actions rather than wildcards. Overly broad permissions frequently cause data exfiltration incidents and automatically fail security review checkpoints on certification tests. Let's check your understanding. Consider a scenario where a user needs to view orders but not process refunds. In a flat RBAC model, you would create a specific role with only the view permission. If you used hierarchical RBAC, you might inherit from a base viewer role and add nothing else. Which approach is better for preventing accidental refund access? Always choose the flatter structure to isolate permissions and avoid unintended privilege escalation during certification scenarios. RBAC offers significant security benefits. By grouping permissions into roles, you enforce least privilege automatically across all assigned identities. It also improves compliance by providing an auditable structure for access management using Azure Policy. Studies show that organizations using RBAC can reduce administrative overhead by up to 40% compared to manual assignment methods. Neglecting this automation typically results in orphaned accounts and failed SOC 2 audits during enterprise assessments. To wrap up, we covered the core components of RBAC and how they interact. We walked through the design process of defining roles, mapping users, and enforcing least privilege. We compared different models to know when to use each one. Finally, we highlighted the security benefits that make RBAC essential for modern systems. Mastering these concepts prevents accidental subscription deletion and ensures you pass the AZ-305 exam with confidence on your first attempt. For the AZ-305 exam, focus on designing RBAC solutions that meet business requirements. You may be asked to identify the best role structure for a given scenario or to troubleshoot access issues using AZ role assignment list. Remember to prioritize least privilege and consider separation of duties for high-security roles. Practice mapping users to roles in complex scenarios involving multiple management groups. Ignoring scope inheritance will cost you critical points on performance-based questions. Imagine a high-security bank where every employee carries a master key that opens every vault forever. If that key is stolen, the damage is instant and total. Now imagine a system where keys are issued only for the exact minutes needed, then returned to the safe immediately after use. That shift from permanent access to on-demand control is exactly what privileged identity management delivers to your cloud environment. In this lesson, we will explore the core philosophy of just-in-time access, walk through the PIM lifecycle model, implement security policies using automation, and review governance best practices essential for the AZ-305 exam. You will learn how to configure eligible role assignments via PowerShell, enforce multi-factor authentication during activation, and monitor audit logs in Azure Monitor. Mastering these steps is critical because standing administrative privileges directly increase your organization's exposure to credential theft. Privileged Identity Management is a cloud-based service within Microsoft Entra ID that enables you to manage, control, and monitor access to important resources. Unlike traditional role assignments that grant permanent standing privileges, PIM operates on a just-in-time model. This means elevated permissions are activated only when needed for a limited duration, typically 2 hours, with a complete audit trail. If you skip this configuration, attackers can exploit dormant admin accounts indefinitely. The primary driver for PIM is reducing the attack surface. Standing privileges are a goldmine for attackers. If a credential is compromised, they have immediate unrestricted access. PIM eliminates this risk by ensuring that even if a password is stolen, the attacker cannot use it to activate a privileged role without passing multi-factor authentication and approval workflows. Failing to enforce these controls leaves your tenants vulnerable to lateral movement during active breaches. PIM follows a strict life cycle. An identity starts as eligible, meaning they have no permissions yet. When work is needed, they request activation. This triggers an approval workflow if configured. Once approved, the role is granted for a specific duration, after which it automatically expires and revokes access. Understanding this exact sequence prevents accidental privilege creep and ensures compliance with strict regulatory audit requirements during certification assessments. Let's look at how we implement this lifecycle through policy. First, we must assign users as eligible for roles rather than granting them directly. You configure these assignments in the Entra ID portal under Privileged Identity Management, selecting specific directory roles like Global Administrator or Exchange Admin. Skipping eligibility configuration immediately creates standing privileges, which violates security baselines and triggers compliance failures during external audits. Here is how we assign eligibility using the Microsoft Graph PowerShell SDK. We connect to Graph with the appropriate scopes, define the user and role IDs, and then invoke new MG Role Management Directory Role Assignment Schedule Request. By setting Schedule Request Type to Admin Assign and specifying a P365D duration, we make the user eligible for 1 year without granting active permissions. This automated approach eliminates manual errors and ensures consistent policy enforcement across large enterprise environments. Next, we move to the activation phase. The user logs into the Admin Center, navigates to My Roles, and clicks Activate. This step triggers the security checks. You must verify that conditional access policies are correctly linked to this process, because bypassing these checks allows unauthorized personnel to escalate privileges without logging any forensic evidence for your security operations team. When the user requests activation, they must provide a business justification, such as a ticket number. This request can trigger an email notification to an IT manager for approval. The role is not granted until the approver reviews and accepts the request, ensuring that elevated access is always authorized. Without this mandatory approval step, you risk granting excessive permissions during routine maintenance windows, leading to accidental configuration drift. Finally, we enforce expiration. The role is automatically revoked after the specified duration, such as 2 hours. This ensures that standing privileges do not accumulate over time. You must configure these time limits carefully, because leaving roles active indefinitely defeats the entire purpose of just-in-time access and exposes your environment to persistent insider threats and compromised session tokens. The expiration is configured at the policy level. For example, you might set a maximum activation duration of 4 hours. Once this time elapses, the system automatically revokes the role assignment. This automated cleanup prevents human error and ensures that access is strictly temporary. If you extend these limits beyond organizational guidelines, you create audit gaps that compliance frameworks will immediately flag during certification reviews. Let's check your understanding. In the PIM lifecycle, what happens if a user requests activation for a global admin role but does not provide a business justification? The system will automatically reject the request and log the failed attempt in the Azure AD audit logs. This validation step is mandatory because it prevents unauthorized privilege escalation and ensures every administrative action remains traceable for security investigations. Remember this principle. Access is a privilege, not a right. By managing it accordingly, you protect your organization from both external threats and internal errors. Always enforce multi-factor authentication during every activation event, configure strict approval workflows for critical roles, and regularly review assignment policies to maintain a secure baseline that passes technical certification assessments. We covered the core concepts of privileged identity management. PIM shifts security from always-on to on-demand access. We explored the life cycle of eligibility, activation, and expiration. We implemented policies using PowerShell automation and reviewed best practices like MFI enforcement and break glass accounts. Mastering these configurations ensures your cloud architecture remains compliant, auditable, and resilient against modern identity-based attack vectors during production deployments. For the AZ-305 exam, focus on these key points. Always enforce multi-factor authentication for role activation. Implement approval workflows for high-impact roles like global admin. Never forget to exclude break glass accounts from PIM policies to ensure emergency access. Finally, monitor audit logs regularly to detect suspicious activity. Understanding these controls directly impacts your ability to design secure identity architectures and pass the performance-based exam questions. Imagine a security guard at a corporate building who not only checks your ID badge, but also notices if you are acting suspiciously or trying to enter a restricted area at the wrong time. That is exactly how Microsoft Entra ID Protection transforms identity security. Instead of relying on static passwords, this feature uses machine learning to analyze billions of signals and detect compromised accounts in real time. You will configure risk policies targeting specific groups like sales. If a sign-in originates from an anonymous proxy, the system flags it immediately. This prevents data breaches and keeps your Azure resources safe. In this lesson, we will explore the core components of Entra ID Protection. We start by understanding the 2 pillars of risk detection. Next, we dive into a step-by-step configuration of risk policies using real examples. Then we look at automation via the Graph API. Finally, we cover essential best practices and common pitfalls to avoid on the exam. You will learn to use the new MG Beta Identity Protection Risk Policy, CMDLET, for sign-in controls. Missing these steps could leave your tenant vulnerable to credential stuffing attacks during certification scenarios. Entra ID Protection operates on 2 primary pillars: risk detections and risk policies. The system continuously analyzes signals from billions of sign-ins across the Microsoft ecosystem to assess risk. These detections are categorized into sign-in risk, which evaluates the probability that a specific authentication request is unauthorized, and user risk, which assesses whether an account has been compromised based on historical behavior. You will configure thresholds like medium or high risk levels. Ignoring these distinctions can cause false positives that lock out legitimate administrators during critical deployments. Let's define the core term. A risk detection is a record generated by the system when it identifies suspicious activity associated with a user or sign-in event. These detections are triggered by specific indicators such as anonymous IP addresses, unfamiliar sign-in properties, leaked credentials found on the dark web, or malware-linked IP addresses. Each detection carries a risk level that determines the automated response. You will see events like auth method password failures in the audit logs. Overlooking these signals allows attackers to maintain persistent access to your Azure AD tenants. Understanding the difference between sign-in risk and user risk is critical for configuration. Sign-in risk focuses on the authentication event itself, such as a login from a new device or location. User risk focuses on the account state, often triggered by leaked credentials. The responses differ too. Sign-in risks typically trigger MFI or block access, while user risks often require a password reset to secure the account. You will configure policies that enforce step-up authentication for medium-risk events. Mixing these up will cause unnecessary help desk tickets and frustrate your end users. Here is how the data flows through the protection system. A sign-in event occurs and triggers signal collection from Microsoft's global telemetry. These signals are fed into the risk assessment engine, which applies machine learning models to calculate a risk level. Based on this assessment, the system triggers the appropriate policy response, such as enforcing MFI or blocking access immediately. You will configure endpoints like Graph, Microsoft, Beta Identity Protection, sign-in risk events to query these events in real time. Failing to monitor this pipeline leaves your environment blind to active credential theft campaigns. Now let's configure a sign-in risk policy. First, we define the assignments to target specific users or groups. You will populate the Include Targets array with object IDs from your Azure AD group like HR team. Crucially, you must add break-glass admin accounts to the Exclude Targets array to prevent being locked out of your own tenant if a false positive occurs. Skipping this step during an exam scenario guarantees you will fail the question on secure access configuration. This JSON snippet demonstrates how to define assignments and exclusions for the policy. We specify the target users or groups in the Include Targets array. Crucially, we add emergency access accounts to the Exclude Targets array to prevent being locked out of our own tenant if a false positive occurs. The structure requires valid GUIDs for both arrays. Misplacing a comma here will cause a 42 HTTP error and block your entire deployment pipeline during live troubleshooting. Next, we set the conditions and access controls. We define the risk level threshold that triggers the policy and specify the action to take when that threshold is met. You will select high as the trigger level and pair it with a block action for severe threats. For moderate events, you might choose MFA instead. Choosing an overly aggressive block policy without testing in report-only mode will disrupt business operations and create massive operational friction. Here is the JSON structure for the conditions and access controls. We set the risk level to high to ensure we only block truly suspicious sign-ins. The policy object defines the action as block, which denies access entirely. For lower risks, you might choose MFA instead. You will validate this payload using Postman before applying it to production. Applying untested policies directly to your tenants causes immediate authentication failures and halts critical development workflows. Finally, we enable the policy enforcement. Once configured, we must turn the policy on to apply it to sign-in events. We also review the policy settings to ensure they align with our security requirements. You will toggle the state property to enabled and verify the is-report-only flag remains false. Forgetting this final step means your carefully crafted rules never actually execute against incoming traffic. This oversight is a classic trap on certification exams testing deployment readiness. This PowerShell command demonstrates how to apply the policy configuration. We use the updatemg identity protection sign-in risk policy (CMDLET) to update the policy state to enabled and save the settings. This ensures the risk detection responses are actively enforced. You will pass the exact policy ID from your tenant and verify the output status matches success. Running this without verifying group memberships first causes unexpected access denials for your entire engineering department during peak hours. Adaptive security shifts your defense from reactive to proactive. By automating responses to risk detections, you reduce the manual workload on your SOC and ensure that compromised credentials cannot be easily exploited. You will implement automated password resets via the resetmg user password CMDLET when user risk thresholds are crossed. Skipping automation leaves your team drowning in repetitive tickets, while attackers slowly exfiltrate sensitive organizational data over weeks. Let's check your understanding. If a user account is detected as compromised due to leaked credentials, which type of risk detection would trigger, and what is the recommended remediation action? You must identify this as a user risk event requiring an immediate password reset and forced sign-out across all sessions. Confusing it with sign-in risk will lead you to select MFI instead of credential rotation. This mistake costs points on scenario-based questions, testing your knowledge of automated remediation workflows. We have covered the essentials of Entra ID Protection. You now understand the two pillars of risk detection and how to configure risk policies step by step. We explored automation with Graph, IPI, and PowerShell, and reviewed best practices like excluding break glass accounts and starting in report-only mode. You will practice these configurations using the Azure portal and CLI before attempting certification labs. Skipping hands-on validation guarantees you will struggle with performance tuning questions on the actual exam day. For the exam, remember that identity protection requires Microsoft Entra ID P2 licensing. Focus on the distinction between sign-in risk and user risk in scenario questions. Always exclude emergency access accounts from risk policies to avoid lockouts. And note that you should start policies in report-only mode before enforcing blocks. You will encounter these exact requirements when configuring conditional access rules for hybrid environments. Ignoring licensing prerequisites or skipping report-only testing guarantees immediate failure on performance-based certification tasks. Imagine you are guarding a medieval castle with a deep moat and a drawbridge. Once you pass through the gates, everyone was trusted. Today's cloud landscape has no physical walls, so that old strategy fails completely. We need a new approach where every single request is verified before access is granted to protect sensitive data. In Azure, configure conditional access in Entra ID to enforce step-up authentication for every sign-in. If you skip verification, attackers will pivot laterally through compromised credentials and exfiltrate your entire tenant. In this lesson, we will explore the core principles of Zero Trust, walk through implementing conditional access policies, compare authentication methods, and review key exam focus areas for your certification. We will cover practical configurations and common pitfalls along the way to ensure you are fully prepared. You will learn to deploy report-only modes before enforcement, configure device compliance checks against Azure AD join status, and avoid blocking executive workflows by misconfiguring exclusions. Mastering these steps prevents accidental lockouts during production rollouts. Let's start with the foundational concept that drives modern cloud security. Zero Trust is a comprehensive security framework that mandates strict identity verification and least privilege access for every user, device, and workload, regardless of network location or origin. This shift eliminates implicit trust in your environment. You must enforce continuous verification using Entra ID Conditional Access rules that evaluate sign-in risk scores before granting access. Failing to validate device compliance or location context allows attackers to bypass perimeter controls and access sensitive tenant resources directly. To build this architecture, you must master 3 core pillars. First, verify explicitly by checking all available data points before granting access. Second, use least privilege access to limit what users can actually do. Third, assume breach and segment your environment to minimize potential damage from attacks. You will configure Entra ID Conditional Access to require multi-factor authentication for every sign-in, restrict admin roles using privileged identity management with just-in-time activation, and isolate workloads via private endpoints. Ignoring segmentation allows lateral movement that compromises your entire subscription. Watch how a typical request flows through this model step by step. The user initiates access, which triggers identity verification against your directory. Next, the system checks device health and location context. Finally, conditional access evaluates these signals to either grant or deny the connection securely. You will configure sign-in risk policies in Entra ID to block high-risk locations automatically, while validating device compliance tags before allowing graph IP calls. Misconfigured evaluation order causes authentication loops that frustrate users and delay critical deployments. First, we identify exactly who needs access and to which cloud applications. We map these targets carefully so our policies only affect the right scope and avoid blocking legitimate workflows. This targeting step prevents accidental lockouts and keeps business operations running smoothly during deployment. You will define specific user groups like global administrators and target cloud apps, including Microsoft 365 and Azure Portal, using the PowerShell CMDLet set as Conditional Access Policy. Skipping precise scoping risks disrupting core ERP integrations and halting production deployments across your tenant. This PowerShell script demonstrates targeting those users and applications. We define the policy state as report, only initially, specify all users and cloud apps in the conditions block, and set the grant controls to require multi-factor authentication. Always deploy and report mode first to validate your targets. You will run getmg conditional access policy to audit existing rules before applying setmg EM conditional access policy with a 90-day enforcement window. Failing to test in report mode causes immediate user lockouts and triggers urgent incident response tickets during peak business hours. Next, we layer in specific security conditions like device compliance and multi-factor authentication. We also integrate identity protection to catch risky sign-ins automatically based on leaked credentials or impossible travel patterns. These controls adapt dynamically to changing threat landscapes and protect your resources effectively. You will configure Entra ID Conditional Access to require compliant devices for SharePoint Online access, while blocking legacy protocols using the setAs AD application CMDLet. Neglecting device compliance checks allows unmanaged endpoints to bypass security boundaries and expose sensitive tenant data. Choosing the right authentication method is critical for your implementation strategy and long-term security posture. SMS-based verification is easy but vulnerable to SIM swapping attacks. The Authenticator app offers strong security with number matching. FIDO2 keys provide phishing-resistant protection for highly sensitive administrative tasks. You will enforce passwordless configurations in Entra ID by disabling legacy protocols and enabling Windows Hello for business across all workstations. Relying solely on SMS credentials exposes your tenant to replay attacks that compromise administrative accounts and breach compliance requirements. This configuration block shows how to enforce passwordless authentication at scale across your organization. We target specific user groups, enable Windows Hello for business, and configure the Microsoft Authenticator app as the primary sign-in method. This eliminates passwords entirely from your primary access vector. You will deploy these settings using the setmg policy authorization policy (CMDLET) while disabling legacy basic authentication protocols via Azure AD Identity Protection. Skipping passwordless migration leaves credential databases exposed to brute force attacks that drain support resources and halt business operations. Finally, we establish continuous monitoring using audit logs and Entra ID Protection. We review sign-in patterns regularly and adjust our policies to adapt to new threats, ensuring the architecture stays resilient over time and maintains strict compliance standards across all environments. You will configure diagnostic settings in Azure Monitor to route conditional access logs to a log analytics workspace with a 30-day retention period. Ignoring continuous monitoring allows dormant compromised accounts to persist undetected, while attackers exfiltrate sensitive data across multiple subscriptions. Keep this core principle in mind as you design your architecture and configure security controls across multiple tenants. Identity is the new perimeter, meaning you must verify every request and trust no network location to prevent unauthorized access. You will enforce strict conditional access rules that evaluate device compliance tags alongside geographic risk scores before granting graph IPI permissions. Failing to treat identity as the primary boundary allows attackers to bypass network segmentation and escalate privileges across your entire cloud infrastructure. Let's test your understanding of these implementation steps and policy configurations carefully. Which Zero Trust pillar focuses on limiting user access to only what is necessary for their specific role? Review least privilege principles before checking the answer. You will evaluate scenarios where administrators require temporary elevation using privileged identity management with a 1-hour activation window. Misapplying broad access controls instead of strict role-based restrictions increases your attack surface and violates compliance mandates during external security audits. Monitoring at scale requires strict governance and automation practices. Review guest access regularly to prevent stale permissions, block legacy authentication protocols entirely, automate policy deployment via graph IPI, and enforce minimum permissions for service principals to reduce your attack surface across the tenant. You will implement automated cleanup workflows using Azure Logic apps that revoke inactive guest invites after 15 days while enforcing least privilege roles on all managed identities. Neglecting governance automation allows permission drift that compromises resource isolation and triggers regulatory fines. We covered the core principles of Zero Trust and walked through implementing conditional access policies effectively across your infrastructure. You learned how passwordless authentication reduces credential theft risk significantly, and why continuous monitoring adapts defenses to evolving threats in modern cloud environments. You will apply these configurations using Entra ID Identity Protection to detect anomalous sign-ins while enforcing device compliance checks on all administrative accounts. Skipping final validation steps leaves your tenant vulnerable to phishing campaigns that bypass legacy security controls. For the AZ-305 exam, focus heavily on conditional access policy structure and exception handling. Know the difference between JIT and JEA access models, understand Entra ID Protection risk detection triggers, and master graph, IP, automation for deploying policies at scale. You will practice configuring report-only modes before enforcement while reviewing risk-based conditions that block high-risk sign-ins automatically. Misinterpreting policy precedents rules during exam scenarios causes incorrect answers about authentication failures and violates secure architecture design principles tested on the certification. Imagine driving down a winding mountain road at night without headlights or guardrails. You might move fast initially, but one wrong turn leads to a crash. That is exactly what running a cloud environment looks like without proper governance. In this lesson, we will explore how Azure Governance provides the essential framework to manage, secure, and monitor your infrastructure at scale while keeping developers productive. Mastering these controls prevents costly misconfigurations and ensures you pass the AZ-104 and AZ-305 exams by understanding exactly how policy inheritance and scope management protect your workloads from accidental exposure or compliance failures. We will start by defining what governance actually means in the Azure ecosystem. Then we will break down the core pillars, dive into policy effects, explore hierarchical scope design, and finish with practical best practices to keep you exam-ready. Each section builds on the previous one, so follow along closely as we map out the exact concepts tested on the certification. Skipping these foundational steps often leads to failed lab scenarios where you misassign management groups or misunderstand compliance states during timed assessments. Before we dive into the mechanics, let us lock in the exact definition you need for the exam. Azure Governance is not just a single tool. It is the complete framework of processes, policies, and tools that you use to manage, secure, monitor, and enforce compliance across your cloud environment at scale. Mastering this terminology will help you quickly eliminate wrong answers during the test. Without this precise understanding, you might confuse governance controls with identity management or networking rules, causing you to select incorrect scope hierarchies when troubleshooting complex multi-tenant deployments. To govern effectively, you must leverage three interconnected pillars. First is Azure Policy, which evaluates resources against business rules. Second is management groups, which provide a hierarchical scope above subscriptions. Third is Blueprints, which bundle policies and templates into repeatable packages. Studies show that automating these three pillars eliminates up to 90% of manual governance overhead, letting your teams focus on building features instead of managing infrastructure. Failing to align these components correctly often results in policy conflicts or orphaned resources that violate your organization's security baseline during peak deployment windows. Governance flows strictly from top to bottom. You apply rules at the management group level, and they cascade down through subscriptions into resource groups, finally landing on individual resources. Understanding this directional flow is critical because inheritance determines how your policies actually behave in production environments. If you accidentally override a restrictive rule at the subscription level without adjusting the parent management group, you will inadvertently expose sensitive data to unauthorized regional endpoints or trigger unexpected billing alerts across all linked tenant directories. Azure Policy uses specific effects to control how rules are applied. Audit Mode logs violations, but allows the action to proceed, making it perfect for testing. Deny Mode actively blocks creation or updates when rules are violated, which is essential for strict security standards. Deploy If Not Exists automatically provisions missing resources before allowing the operation, ensuring required components always exist. Confusing these effects during a performance-based exam question will cause you to misconfigure enforcement timelines or accidentally lock out critical deployment pipelines when enforcing mandatory encryption standards across storage accounts. Let us walk through how you actually enforce a standard like mandatory cost center tagging. First, you define the policy rule in a JSON file that checks for the missing tag. Next, you assign that policy to your target subscription or management group. Finally, you validate the enforcement by running a compliance query to see which resources are already out of spec. Skipping this validation step often leaves untagged virtual machines running in production, which directly prevents accurate cost allocation and triggers automated remediation failures across your financial reporting dashboards. Here is the exact JSON structure you will see on the exam. The policy rule evaluates a condition where it checks if the cost center tag field exists and returns false. When that condition triggers, the effect is set to deny, which immediately blocks the resource creation until the developer adds the required tag. Misreading this conditional logic during timed assessments frequently leads candidates to select incorrect parameter values or overlook how Azure Resource Manager evaluates tags before provisioning compute instances in restricted regions. Remember this principle as you study for the certification. Governance is never about stopping development or creating bureaucracy. It is designed to empower your engineering teams to move quickly and safely within defined boundaries, ensuring that speed never compromises security or compliance. Ignoring this mindset during practical lab exercises often results in overly restrictive policies that block legitimate deployment pipelines or force developers to bypass critical access controls, ultimately increasing your organization risk exposure across all managed environments. Let us pause and check your understanding. If you need a rule that automatically provisions a missing resource before allowing the main operation to proceed, which policy effect should you choose? The correct answer is Deploy If Not Exists, which handles the provisioning step automatically behind the scenes. Choosing Audit Only or Deny for this specific scenario will completely halt your deployment workflow and prevent essential monitoring agents from installing correctly on newly created virtual machine scale sets during automated scaling events. As you implement these controls, follow proven best practices to avoid common traps. Always start new policies in audit mode to see impact without breaking workflows. Group related rules into policy initiatives to simplify management. Avoid overgoverning by keeping rules necessary and clear, and automate everything using infrastructure as code to maintain version control. Neglecting these steps frequently causes policy drift across multiple subscriptions, which forces administrators to manually reconcile compliance states and increases the likelihood of accidental permission escalation during routine maintenance windows. Identity governance is equally important. Here is a practical as-role definition. Create command to establish custom roles with least privilege access. We define the name and description, specify read-only actions for authorization resources, and scope it directly to a specific subscription to prevent permission creep. Failing to restrict these custom roles to exact resource groups often results in global contributor assignments that bypass governance controls and allow unauthorized users to modify critical networking configurations across your entire tenant directory. We covered a lot of ground today. Governance ensures compliance and security at scale by using hierarchical scope inheritance. You must match specific policy effects like deny or audit to your operational goals, and you should always automate governance structures using infrastructure as code alongside strict role-based access control. Overlooking these interconnected components during certification assessments frequently leads to misaligned scope definitions that fail to enforce mandatory encryption standards or incorrectly route compliance reports across disconnected management group hierarchies in production environments. For the AZ-305 exam, focus heavily on understanding the exact behavior of each policy effect and how management groups cascade rules down. Practice scoping RBAC roles correctly to avoid permission sprawl, and review how blueprints bundle artifacts together. Master these fundamentals to pass with confidence. Missing these specific technical details during timed performance tasks often causes candidates to misconfigure assignment scopes or overlook critical compliance state transitions, which directly impacts your ability to design secure multi-tenant architectures under strict time constraints. Imagine driving a car at night without headlights, trying to steer through a maze of blind alleys. That is exactly what managing hundreds of subscriptions without management groups feels like. You are flying blind, risking collisions everywhere. Management groups act as your bright headlights and clear zoning districts, allowing you to set traffic rules once at the district level so governance automatically flows down to every resource inside, keeping your production environment safe and visible. In this lesson, we will master management groups by comparing 3 hierarchy design models like environment versus hybrid approaches. Then walk through implementing a scalable structure using Terraform code blocks with specific resource identifiers. We will review critical best practices to avoid exam pitfalls, ensuring you can confidently architect secure tenant topologies that align with organizational security boundaries and cost reporting requirements for the AZ-305 certification. Management groups provide the highest governance scope, below the tenant root group, organizing subscriptions into a hierarchical tree where policies and role assignments inherit strictly downward. This inheritance mechanism saves massive administrative overhead. For example, assigning a deny write storage blob policy at the parent level automatically blocks write operations across all linked child subscriptions without manual configuration on each individual resource, preventing accidental data modification in critical workloads. A management group is a logical container that holds subscriptions and other management groups, serving as the highest organizational unit you control within the Azure tenant hierarchy. It sits directly under the tenant root group, which is managed exclusively by the global administrator. Understanding this boundary is vital for exam scenarios involving cross-tenant governance, as you cannot move subscriptions directly into the tenant root group without explicit global privileges. When designing your hierarchy, you generally choose between 3 models. The environment model separates resources by lifecycle stages like production versus development. The business unit model mirrors your organizational chart with distinct nodes for each department. The hybrid model combines both approaches and is the recommended pattern for mature enterprises, allowing you to balance centralized platform control with decentralized business unit autonomy while maintaining consistent security baselines across all scopes. Here is how a hybrid model flows in practice. You start with the tenant root group, then branch into shared platform services like identity and networking. From there, you split by business units such as finance or engineering, and finally nest environments like production under each unit. This structure ensures policies flow logically from platform governance to specific business needs, preventing configuration drift across diverse operational teams. Let's walk through the process of designing and implementing this hierarchy effectively. First, we map your business structure to tree nodes by identifying key decision-making authorities and security boundaries. This mapping ensures alignment with operational workflows, allowing you to create precise management group names that reflect actual departments or environments, which simplifies auditing and cost allocation tracking for finance stakeholders reviewing monthly subscription usage reports. Mapping your structure requires analyzing how decisions are made in your organization to determine the optimal node placement. Identify which teams own resources, where strict security boundaries exist for data isolation, and how costs are reported for chargebacks. This analysis dictates whether you create nodes for specific departments or just environments, ensuring the hierarchy reflects reality rather than arbitrary groupings that complicate policy inheritance and access control reviews during audits. Next, we move to implementation using infrastructure as code tools like Terraform or Bicep to ensure repeatability and version control. You define management group resources with unique identifiers and parent references in your code files, then apply these definitions via automated pipelines. This approach eliminates manual errors in the Azure portal and guarantees that your governance structure remains consistent across development, staging, and production environments when you deploy updates. This Terraform snippet shows how to build the hierarchy programmatically using the Azure Management Group resource. First, we define a root management group with a clear name like Contosero T. Next, we create a child group for production, explicitly linking it to the root using the parented parameter pointing to the root's object ID. Finally, we associate a specific subscription via Azure subscription to that production group, ensuring the tree structure is complete and ready for governance assignments. Finally, we apply governance by assigning policies and RBAC roles at the appropriate management group levels to enforce compliance without over-provisioning access. For instance, you might assign a contributor role to a platform team at the root level while restricting subscription creation to specific security groups in child nodes. This layered approach ensures that permissions follow the hierarchy, preventing accidental privilege escalation and maintaining strict control over resource lifecycle operations across the tenant. Remember this principle. Inheritance is your greatest governance tool for scaling operations efficiently. By placing policies at the appropriate management group level, you ensure that all current and future subscriptions automatically inherit the necessary guardrails without manual intervention. This consistency keeps security baselines intact as you onboard new workloads, preventing configuration drift and ensuring that every resource complies with organizational standards regardless of where it is created within the hierarchy structure. Let's check your understanding with a critical exam scenario. Which pitfall should you avoid when designing your hierarchy to prevent accidental global impacts across the entire tenant? Consider the risks of placing restrictive policies at the tenant root group or assigning broad RBAC roles too high in the tree, which could inadvertently lock down essential services or restrict access for legitimate operations across all connected subscriptions simultaneously. To recap, management groups provide the essential scope for governance at scale within Azure subscriptions. Your hierarchy should reflect your business structure through models like hybrid design to balance control and autonomy. Use infrastructure as code to deploy structures consistently and repeatably across environments. Remember that inheritance allows you to apply policies once at parent nodes for automatic enforcement across the entire tree, ensuring compliance without redundant manual configurations. For the AZ-305 exam, focus on these critical details. Keep your hierarchy shallow, adhering to a maximum depth of 6 levels, including the tenant root group, to avoid complexity penalties. Avoid the root trap by never assigning resources directly to the tenant root group. Use management groups instead. Finally, always use policy exemptions for specific exceptions rather than moving subscriptions to less governed groups, which breaks inheritance and creates security gaps during audits. Picture an air traffic controller managing a busy airport without radar. Every plane is a guess, runways are shared chaotically, and safety is left to chance. In Azure, your subscriptions are those runways. A subscription strategy is the blueprint that organizes billing, security, and resources so they scale predictably instead of collapsing into sprawl. Today, we will design a robust strategy using management groups and policy definitions that keep your cloud environment secure, compliant, and manageable as you grow beyond initial pilot deployments. Here is our plan for the lesson. We will start by exploring the 4 pillars that drive every subscription design decision. Then, we will compare different strategies like environment-based versus project-based models to see which fits your needs. Next, we will walk through the procedure of designing governance with management groups and policy definitions. Finally, we will cover best practices and common pitfalls to avoid on the exam, ensuring you can architect scalable multi-tenant environments without hitting service quota limits or causing unauthorized access breaches. A well-architected subscription strategy rests on 4 primary pillars. First is billing and cost tracking, which determines how you break down spend by department or project using cost management workbooks. Second is access control via RBAC, where subscriptions act as the ultimate security boundary for who can manage resources. Third is governance through Azure Policy, allowing you to enforce guardrails across multiple tenants. Fourth are service limits and quotas. Every subscription has hard ceilings, like 1,500 vCPUs per region, that dictate how you distribute workloads before hitting throttling errors. When designing your strategy, you must choose a model that fits your organization. An environment-based approach separates subscriptions by stage, such as production versus development, which is common for mid to large enterprises managing distinct life cycles. A project-based model isolates workloads by business unit or application, making it easier to track costs per deliverable using dedicated resource groups. A department-based strategy aligns subscriptions with organizational structure, simplifying chargebacks. You often combine these models to meet complex governance needs without creating unmanageable sprawl. Visualizing the hierarchy helps you understand how scope flows. At the top sits the root management group, which inherits from Azure and contains all subscriptions in your tenant. Below that, you create logical groups like production or corporate using the as-mg create command. Subscriptions are placed at the leaves of this tree. This structure allows you to apply policies and role assignments at the group level, automatically cascading them down to every subscription beneath it, preventing configuration drift across hundreds of accounts. Let's define a critical term, the management group. A management group is a logical container that helps you manage access, policies, and compliance across multiple subscriptions. Think of it as a folder for subscriptions. When you apply a policy to a management group, every subscription inside that group inherits the policy. This is how you enforce governance at scale without touching each subscription individually, saving hundreds of administrative hours and preventing costly misconfigurations during rapid scaling phases. Now let's design the governance hierarchy step by step. First, we build a management group tree that reflects your organization's structure. This establishes the backbone for all subsequent policies and access controls. You will create parent groups like L1 and L2 using PowerShell or CLI commands, then link existing subscriptions to those leaves. This foundational layout ensures every downstream policy assignment targets the correct scope, preventing orphaned resources from slipping through security gaps during high-volume deployments. Here is how you implement the first step using infrastructure as code. This bicep snippet creates a new subscription and assigns it directly to a management group. We define the subscription with a display name and an alias, then use the resource provider to link it to the target management group. This ensures the subscription is born into the correct hierarchy with no manual steps, eliminating configuration drift and guaranteeing immediate policy enforcement from the moment the tenant account activates. Next, we enforce Azure Policy to establish guardrails. Once the hierarchy exists, we apply policies that prevent non-compliant resources from being created, ensuring data sovereignty and cost control automatically. We will define policy definitions with explicit deny effects, then assign them at the management group scope. This automated enforcement stops developers from accidentally deploying unencrypted storage accounts or exceeding budget thresholds, keeping your infrastructure compliant without requiring constant manual audits or security reviews. This JSON snippet defines a built-in policy that restricts resource creation to specific locations. The policy rule checks the field for location and denies any resource not in the allowed array. By applying this at the management group level, every subscription under it inherits this restriction, preventing accidental deployments in unauthorized regions. You will see immediate failure responses when teams attempt to spin up virtual machines in blocked data centers, protecting your compliance posture and avoiding unexpected cross-border data transfer fees. Finally, we apply least privilege RBAC to manage access. We assign roles at the lowest level necessary, avoiding broad permissions like owner or contributor at the subscription level unless absolutely required. You will configure role assignments targeting specific resource groups or virtual machines instead of granting tenant-wide administrative rights. This granular approach prevents credential compromise from cascading across your entire environment, ensuring that a single leaked key cannot trigger mass deletions or unauthorized billing changes. Here is a bicep snippet that assigns a contributor role to a user on a specific resource group, rather than the entire subscription. We define the role definition ID for contributor and scope it to the resource group. This ensures the user can manage resources in that group without having control over other parts of the subscription. You will execute this assignment using the NewAz role assignment command, which immediately restricts permissions to the designated workload and prevents accidental tenant-wide outages during routine maintenance. Remember this principle: policy is law. Never rely on process to enforce compliance when you can use code. If a rule isn't enforced by Azure Policy, it is not truly governed. Design your policies to deny non-compliant actions automatically, keeping your environment secure without manual intervention. You will configure policy definitions with explicit deny effects and assign them at scale, ensuring that every deployment pipeline fails immediately when violating security baselines or budget thresholds across your entire tenant. Let's check your understanding. You are designing a subscription strategy for a company with strict data residency requirements. Which approach ensures that resources cannot be created in unauthorized regions? A. Using tags for cost tracking. B. Applying a deny policy at the management group level. C. Creating a sandbox subscription. D. Assigning owner role to developers. The correct answer is B, because management group scope enforcement automatically blocks non-compliant deployments before they consume compute resources or violate regional compliance mandates. To recap, subscriptions are your primary mechanism for billing, security, and quota management. Always use a management group hierarchy to manage subscriptions at scale, avoiding the one subscription trap. Apply Azure Policy to enforce guardrails automatically, and design RBAC with least privilege in mind. Plan your hierarchy early, as reorganizing subscriptions later is complex and risky. You will save hundreds of hours by structuring policies correctly from day one, preventing costly service limit exhaustion and ensuring audit-ready compliance across every department. For the AZ-305 exam, focus on these tips. You will be asked to design a subscription strategy that balances autonomy and control. Know how to use management groups to apply policies to multiple subscriptions. Understand the difference between environment-based and project-based strategies. Remember that service limits can cause outages if you put everything in one subscription. Always choose the solution that enforces governance through code rather than manual processes, ensuring you score points on scenario questions requiring scalable, auditable architectures. Imagine walking into a massive warehouse where every single box is labeled stuff. You need a specific invoice, but you have no idea which aisle holds it, or worse, accidentally toss the whole crate because you thought it was empty. That is exactly what happens in Azure when you ignore resource group organization. Without clear structure, your cloud environment becomes a digital landfill where tracking costs, managing permissions, and deploying updates quickly becomes a nightmare for any administrator. In this lesson, we will explore core organization patterns for resource groups, walk through implementing them using bicep modules, review critical governance best practices to avoid common pitfalls, and finish with specific exam tips for the AZ-305. Mastering these structures prevents costly misconfigurations during certification exams and ensures your production deployments scale reliably across multiple teams. A resource group is a logical container that holds related resources for an Azure solution. It acts as the fundamental lifecycle boundary, meaning all resources within a group are deployed, updated, and deleted together using commands like as-group-delete. You use resource groups to manage role assignments, apply policies, and monitor application health in one unified view, preventing accidental deletion of critical production workloads during routine maintenance. Choosing the right pattern depends on your operational model. The lifecycle-based pattern groups resources by environment like dev or prod, which is essential for strict security boundaries enforced by Azure Policy. The workload-based pattern organizes resources by specific application, ideal for microservices where teams need independent management. You might also use functional patterns for departmental budgets or geographic patterns for data sovereignty compliance, preventing costly audit failures during certification scenarios. Here is a bicep template that enforces a standardized naming convention and mandatory tagging. We define parameters for the environment, application name, and location to ensure every deployment is consistent. The resource block creates the group using a dynamic name derived from those parameters. Inside the tags block, we enforce critical metadata like environment and cost center, which Azure Policy can later validate to prevent drift and stop unauthorized spending. Let's compare these patterns side by side to see where they fit best. The lifecycle pattern is perfect for strict security isolation between environments using separate subscriptions. The workload pattern shines for microservices and independent team ownership with dedicated resource groups. Functional patterns help when departments manage their own budgets, while geographic patterns are mandatory when data residency laws require specific regions, preventing compliance violations that trigger immediate executive review. When deciding which pattern to apply, follow this decision flow. First, assess your application dependencies and team structure to see if workloads are tightly coupled. Next, check for compliance needs that might force a geographic split across Eastis and Westis too. Then, define the lifecycle requirements to determine environment boundaries. Finally, assign the resource group based on these inputs to ensure governance aligns with your operational reality and avoids permission sprawl. First, we standardize naming conventions to ensure every resource group follows a predictable structure that reflects its purpose and environment. This eliminates confusion and makes automation reliable. We typically enforce prefixes like rgprodapp or rgdev analytics using Azure CLI scripts, preventing accidental overwrites of critical infrastructure during rapid development cycles and ensuring auditors can instantly locate assets. This bicep snippet demonstrates the naming convention in action. We use parameters to inject the application name and environment into the resource name string. This ensures that every deployed group immediately carries meaningful metadata without manual intervention. For instance, passing dev and webfrontend generates a predictable identifier like rgdev webfrontend, which streamlines troubleshooting and prevents cascading failures during automated rollback procedures. Next, we enforce mandatory tags via Azure Policy to prevent permission creep and ensure cost tracking is always accurate. This step guarantees that no resource group can be created without the required metadata for governance. We typically require owner email and project code fields, stopping unauthorized spending before it impacts your monthly invoice and keeping compliance audits strictly within acceptable thresholds. Here is an Azure policy definition that enforces mandatory tags. The policy rule checks for the presence of environment and cost center tags during creation. If either tag is missing, the deployment fails immediately, ensuring strict compliance with your governance standards. For example, blocking a VM without these tags prevents orphaned compute instances from draining your subscription budget unnoticed. Finally, we automate deployment with SI/CD pipelines to ensure every resource group is created consistently. This removes manual errors and scales governance across your entire organization automatically. We configure Azure DevOps YAML files to trigger on pull requests, guaranteeing that infrastructure changes undergo peer review before reaching production environments and eliminating configuration drift across multiple regions. This YAML pipeline demonstrates the automation step. It triggers on code changes and uses the Azure Bicep task to deploy the standardized template. The pipeline passes parameters for environment and application name, ensuring every deployment follows the governance rules we defined. For instance, setting a timeout of 30 minutes prevents hung deployments from consuming agent capacity during peak build windows. Governance is continuous. Use Azure Policy to audit and enforce your organization patterns automatically. If a resource group doesn't meet the standard, the system should flag it or remediate it immediately. We recommend configuring automatic compliance scans every hour, which catches drift before it escalates into security breaches and keeps your certification exam answers aligned with real-world operational rigor. Let's check your understanding. Which pattern is best for a microservices architecture where teams need independent management and cost allocation? Think about the options we discussed. The answer is the workload-based pattern, as it allows teams to manage their specific application stacks without affecting others. For example, isolating payment services in separate groups prevents billing confusion during monthly reconciliation and keeps audit trails perfectly clean. Avoid God resource groups containing over 500 resources, as portal performance degrades significantly when querying large datasets. Always enforce tagging policies to prevent permission creep and use separate subscriptions for hard security boundaries. Keep lifecycle synchronized by never mixing production and non-production resources in the same group, which prevents accidental deletion of critical databases during routine maintenance windows. We covered lifecycle and workload patterns, implemented governance with BICEP and policies, and reviewed best practices like avoiding God resource groups. Remember that naming conventions are mandatory, tags provide essential metadata, and governance requires continuous auditing to keep your cloud environment scalable and secure. Mastering these fundamentals ensures you pass the AZ-305 exam while building resilient infrastructure for enterprise clients. Focus on the exam tips. Lifecycle is king for security boundaries, naming conventions prevent chaos, tags enable cost tracking, and governance must be automated. Right-size your containers by balancing security risks against management overhead, and use subscriptions for distinct compliance requirements. Practice configuring Azure Policy definitions with AZ-CLI commands to master the practical scenarios tested on certification day. Imagine driving on a highway at night without guardrails. One drift and you are off the cliff. In Azure, your applications are those vehicles, and your cloud environment is the road. Azure Policy acts as the essential guardrails that keep every deployment within safe boundaries. For example, you can use it to mandate ESTIS regions for all virtual machines, preventing costly data residency violations. Without these automated checks, teams will accidentally spin up expensive resources or leave storage accounts publicly accessible, breaking compliance and draining your budget. We will systematically break down Azure Policy governance by starting with its core service architecture and evaluation engine. You will learn to craft custom policy definitions using ARM templates and manage them through the As Policy Definition CLI command. We will map out assignment scopes ranging from management groups down to individual resource groups, then compare enforcement effects like audit versus deny. Mastering this workflow prevents orphaned resources and ensures your compliance checks run predictably across every subscription before certification day. Azure Policy is a centralized governance service that continuously evaluates resource configurations against defined rules and reports compliance status. You apply these rules at the management group level, allowing inheritance to flow downward through subscriptions and resource groups. For instance, you can enforce mandatory tagging on all virtual networks by specifying required metadata fields. If you skip this evaluation step, developers will deploy untagged assets that become impossible to track during billing audits or security incident investigations across your tenant. Mastering this service requires a strict three-step workflow that moves from rule creation to active enforcement. You begin by writing the policy definition JSON schema, then assign the initiative to a specific subscription scope using the portal or CLI. Finally, you trigger remediation tasks to automatically patch non-compliant configurations. Skipping the assignment phase leaves your environment unmonitored, causing critical security gaps to persist while auditors flag missing controls during compliance reviews. The first phase focuses on crafting the policy rule JSON with precise conditional logic. You structure the if block to check Microsoft Compute virtual machines against a parameter array containing standard D2S v3 and standard D4s v3. The then block immediately applies a deny effect when the condition fails. This exact configuration stops unauthorized large instance deployments before they consume quota, preventing unexpected billing spikes and ensuring your infrastructure stays within approved engineering limits. After defining the rule, you attach it to a governance scope that dictates evaluation boundaries. Assigning the policy at the root management group level propagates the rule across every child subscription and resource group automatically. You can verify inheritance using the As Policy Assignment List command. Placing assignments too deep in the hierarchy creates conflicting rules that override parent controls, causing enforcement failures and leaving critical workloads exposed to unauthorized configurations. The governance hierarchy flows strictly downward from management groups to subscriptions, then resource groups, and finally individual resources. You assign policies at the top level to ensure automatic inheritance across all child scopes. For example, attaching a storage encryption rule to a management group instantly applies it to every subscription below. Misordering this hierarchy causes policy conflicts where lower scope assignments override higher controls, breaking your centralized compliance framework and triggering audit failures. The final phase handles remediation and active enforcement for existing non-compliant resources. You configure the policy to automatically apply missing tags or deploy required diagnostic extensions using background tasks. For instance, triggering a remediation task on a virtual machine network interface instantly attaches the approved security group. Ignoring this step leaves historical drift uncorrected, allowing deprecated configurations to accumulate until they trigger compliance violations during routine security assessments. Treat all governance rules as version-controlled code stored in a Git repository with mandatory peer review. You deploy policy definitions through Azure DevOps pipelines using the As policy definition, create command, ensuring every change receives traceable approval. This structured approach prevents accidental removal of critical controls and guarantees that compliance standards remain synchronized across development, testing, and production tenants without manual intervention. The audit effect logs violations in the activity stream without blocking deployments, while deny actively rejects non-compliant requests at creation time. Modify automatically patches properties, like adding required tags, and deploy if not exists provisions missing resources, such as log analytics workspaces for monitoring. Choosing the wrong effect causes either workflow paralysis or silent compliance drift, directly impacting your ability to pass security audits and maintain operational stability. Use initiatives to bundle related policy definitions into a single assignable package targeting specific compliance frameworks. You create an initiative definition containing multiple policy rules, then assign the entire group to a management group for unified tracking. This grouping mechanism simplifies reporting by consolidating individual rule statuses into one dashboard view. Failing to use initiatives forces administrators to track dozens of separate assignments, increasing configuration errors and slowing down remediation cycles significantly. Let me test your practical knowledge with a scenario you will encounter on the certification exam. You need to strictly prevent developers from deploying virtual machines in an unauthorized region like Westis 2. Which enforcement effect should you select to block the deployment immediately at creation time? The correct answer is deny, because it actively rejects non-compliant requests before provisioning begins, whereas audit only logs violations and leaves your environment vulnerable to policy drift. Jumping directly to deny mode in production environments creates immediate workflow disruption and breaks existing deployments. You should always enable audit first to identify non-compliant resources without blocking traffic, then switch to deny after confirming all workloads meet the new standards. This phased approach prevents sudden service outages and gives engineering teams time to adjust their infrastructure templates before strict enforcement begins. Azure Policy serves as the central governance engine for enforcing standards across your cloud footprint through structured rule evaluation and scope inheritance. You design custom definitions with specific JSON logic, assign them to management groups or subscriptions, and bundle related rules into initiatives for unified tracking. Following the audit before deny pattern ensures smooth adoption, preventing accidental service breaks while maintaining strict compliance throughout every deployment lifecycle. Remember that policy evaluation requires up to 30 minutes to propagate across existing resources after initial assignment. Focus heavily on distinguishing enforcement effects during scenario questions, knowing that audit logs violations without blocking, deny actively rejects non-compliant deployments, modify patches properties automatically, and deploy if not exists provisions missing diagnostic extensions. Mastering these distinctions prevents you from selecting incorrect answers when evaluating compliance scenarios under timed conditions. Picture an airport control tower without radar. Every flight is a guess, and the risk of collision is high. In Azure, governance acts as that radar system, managing virtual machines and storage accounts instead of aircraft. Custom policy definitions let you write strict rules that keep your cloud environment secure by design. If you skip this step, engineers will spin up unencrypted SQL databases in open regions, triggering massive compliance fines. Mastering these tools shifts you from reactive firefighting to proactive enforcement before the exam or production launch. In this lesson, we will break down the anatomy of a policy definition, walk through the safe lifecycle for enforcing rules, and see how initiatives bundle these controls together. We will also cover the common pitfalls that trip up candidates on the AZ-305 exam. You must understand parameter passing and scope inheritance to avoid accidentally locking down your entire management group. Missing these details will cost you points on scenario-based questions, where you need to recommend the correct governance approach for a multi-subscription enterprise. Let's start with the core building block. A policy definition is essentially a JSON file that describes a rule. It contains three main parts: the policy rule logic that evaluates compliance, parameters that make the rule reusable across different environments, and metadata like display names for management. If you misplace a comma inside the condition block, Azure will reject the entire definition during deployment. Understanding this structure matters because exam questions frequently test your ability to spot syntax errors in complex JSON payloads under time pressure. Here is a real-world example of a custom policy definition. This JSON restricts resource creation to specific locations for data residency compliance. Notice the policy rule section. It uses an if statement to check the location field against your allowed parameters. If the condition is met, the then block applies a deny effect, blocking the deployment. You would create this using the as policy definition, create command, and specify exactly 3 allowed regions. Failing to validate this logic could allow sensitive workloads to deploy in unauthorized jurisdictions. Before we enforce these rules, you need to understand the available effects. The audit effect logs violations without blocking anything. Deny actively blocks non-compliant deployments. Deploy if not exists triggers a remediation task to fix the resource, and modify updates properties automatically. Choosing the right effect is critical for your exam. If you accidentally apply deny to a core networking policy, you will immediately break connectivity across your entire subscription. Always verify the impact scope before publishing any effect change to production. Now let's look at the safest way to roll out these policies. We follow a 3-step lifecycle to ensure we don't break production. First, we enable the audit effect to identify non-compliant resources without disrupting business operations. This phase typically takes 48 hours to fully scan your existing resource graph. Skipping this careful evaluation means you could accidentally lock out critical application servers during peak business hours. Documenting each step protects your team from unexpected downtime and compliance audits. In this phase, you deploy the policy with an audit effect. The system evaluates your existing resources and logs any that violate the rule in the activity log. This gives you a clear inventory of what needs fixing without stopping any new deployments or breaking current workflows. You will see detailed compliance records appear within 20 minutes of assignment. If you ignore these early warnings, technical debt will accumulate rapidly, making future remediation exponentially more expensive and difficult to track. Once you have your list of violations, the next step is to remediate them. You can use automated scripts or Azure Policy remediation tasks to bring existing resources into compliance based on the audit findings. This process typically scans approximately 500 virtual machines per batch to avoid overwhelming your subscription limits. Failing to throttle these background operations could trigger throttling errors and stall critical CI/CD pipelines across your engineering teams. Here is how remediation works in practice. You can trigger a remediation task that runs alongside your policy. This task reads the audit logs and applies the necessary changes to fix non-compliant resources, such as adding missing tags or updating configurations, effectively cleaning up the environment. The system will generate a detailed progress report showing exactly 3% completion per hour. If you do not monitor these background jobs, stale tasks will consume quota limits and leave critical security gaps unpatched. After you have fixed the existing issues and verified that your remediation tasks are working, the final step is to switch the policy effect to deny. This locks down the environment, ensuring that no new non-compliant resources can be created or updated. You should schedule this transition during a scheduled maintenance window to prevent accidental deployment failures. Skipping proper validation at this stage will immediately block legitimate developer deployments and halt your entire release pipeline. In this final phase, you update the policy definition to use the deny effect. Now, any attempt to create or update a resource that violates the rule will be blocked immediately. This provides true enforcement and ensures your infrastructure remains compliant by design. You will execute this change using the As Policy Definition update command with a 45-second timeout for validation. Failing to test this restriction in a separate sandbox subscription could permanently lock out automated deployment agents and cause severe service interruptions. This brings us to a key principle: governance as code. Treat your policies like software. Use version control, peer reviews, and automated testing to manage them. This ensures that your governance rules evolve safely alongside your applications. You should store every JSON definition in a dedicated repository and enforce pull request approvals before merging changes. Ignoring this disciplined workflow will cause configuration drift and make it nearly impossible to trace which engineer introduced a breaking compliance rule last week. Now let's look at how we manage these policies at scale using initiatives. An initiative is a wrapper that groups multiple policy definitions together. This allows you to assign a suite of related rules, like an ISO compliance set, as a single unit to a scope, simplifying management and reporting. You will typically bundle around 20 individual rules into one custom initiative package. Forgetting to map the correct resource group scope will cause the entire compliance dashboard to report inaccurate 0% status across your financial workloads. Let's check your understanding. You need to enforce a rule that blocks non-compliant deployments immediately. Which effect should you use in your policy definition? Think about the options we discussed earlier. The correct answer is strictly deny, because only that effect actively prevents resource creation during validation. If you mistakenly select audit for this scenario, attackers will successfully deploy unencrypted storage accounts and expose sensitive customer data without triggering any immediate alerts. To recap, we covered the structure of policy definitions and saw how to restrict resources using JSON rules. We walked through the safe audit lifecycle to enforce policies without breaking production. Finally, we explored how initiatives bundle these rules for easier management. Mastering these concepts directly impacts your ability to pass the AZ-305 exam by demonstrating practical cloud governance skills. Skipping this foundational knowledge will leave you unable to design secure multi-tenant architectures or troubleshoot complex compliance failures during troubleshooting scenarios. For the AZ-305 exam, focus on reading JSON policy definitions and understanding the differences between effects. You might be asked to choose the right effect for a scenario or identify how to safely enforce a new rule. Remember the audit lifecycle. Audit first, remediate, then deny. Practicing with exactly 20 sample questions will build your speed for identifying parameter mismatches. Ignoring these specific testing strategies will cause you to misread critical compliance constraints and waste valuable minutes on complex scenario questions. Imagine a library where any visitor could randomly delete or rewrite the books on the shelves. Chaos would ensue instantly, and valuable information would vanish without a trace. In cloud governance, we face a similar risk. Resources are dynamic and ephemeral, managed by multiple teams who might accidentally break critical infrastructure. Today, we will explore how to build a safety net using resource locks and establish a metadata backbone with tagging strategies to keep your environment secure, cost-effective, and aligned with business objectives. We begin by examining how Azure Resource Manager locks shield your infrastructure from accidental deletion. Next, we will master tagging fundamentals to guarantee operational visibility across every subscription. Then, we will walk through exact implementation steps using the Azure CLI and Terraform providers. Finally, we will cover policy enforcement best practices to help you avoid governance gridlock during the AZ-305 exam and keep production costs predictable. Let us define our primary tool, resource locks. These are declarative Azure Resource Manager controls that prevent accidental deletion or modification of live cloud assets. They act as a hard safety net, ensuring that even if an operator or automated script attempts to remove a critical asset, the platform will immediately reject the request. You can apply these locks at the resource group, or subscription level to enforce strict boundaries around your infrastructure and prevent costly downtime. There are two distinct lock types you must master for the certification exam. First, read-only allows authorized users to view the resource but blocks any updates or deletion. Second, cannot delete permits reading and modifying the resource, which is essential for ongoing operations, but strictly prevents deletion. Understanding this distinction is crucial because production environments often need updates without risking accidental removal, and misapplying them can trigger deployment failures across dependent services. Before we dive into implementation, let us check your understanding with a practical scenario. Consider a production Azure SQL database that requires frequent updates by the DevOps team, but it must never be deleted under any circumstances. Which lock type should you apply to this specific resource? Think carefully about the trade-off between modification rights and deletion protection, because selecting the wrong option will block routine maintenance and halt your deployment pipeline. Here is how you apply a cannot delete lock using the Azure CLI in your terminal. You will run azlock create with the exact scope flag pointing to your resource group. Notice the comments explaining each parameter. The name identifies the lock, the type enforces the restriction, and the target ensures the protection applies to all resources within that container. Misconfiguring the scope can leave critical compute instances exposed to accidental termination during routine maintenance windows. Tags are key-value pairs that act as the primary index for your cloud ecosystem. This table compares common tag keys and their exact purposes. Owner establishes accountability, environment isolates workloads, cost center tracks finance, project provides context, and automated shutdown triggers lifecycle scripts. Consistency here is vital because inconsistent keys lead to reporting failures and orphaned resources, which directly inflates your monthly Azure subscription bills and complicates audit compliance. A robust tagging strategy requires a strictly standardized taxonomy across your entire organization. You must define keys early to avoid messy naming conventions, where teams use inconsistent names, like department versus department. Enforce this via Azure Policy to deny resource creation if mandatory tags are missing. Additionally, automate cleanup for untagged resources after a strict grace period to prevent cost leakage and operational chaos during month-end financial reviews. Now let us implement these controls systematically within your deployment pipeline. First, we define a standardized schema for all tags to ensure consistency across the organization. This step establishes the metadata backbone that downstream processes will rely on for accurate cost allocation and automated lifecycle management. Skipping this phase guarantees that financial reporting tools will fail to aggregate data correctly, leaving you blind to actual spending trends. This Terraform configuration demonstrates enforcing a tagging schema directly on a virtual machine resource block. The code explicitly sets the tags argument with environment, owner, cost center, and managed by keys using exact string values. By using infrastructure as code, we ensure that every deployed resource automatically inherits these standardized metadata values, preventing manual drift and guaranteeing that billing exports match your internal chargeback requirements perfectly. Next, we apply targeted locks to protect critical resources within your active subscription. After establishing your schema, you must secure the infrastructure by applying cannot delete or read-only locks at the appropriate scope using automated scripts. This step ensures that even with a solid tagging strategy, your assets remain safe from accidental deletion, preventing catastrophic service outages when junior engineers accidentally run cleanup commands against production workloads. Here is a policy definition that strictly enforces tagging requirements across your management group. The JSON structure specifies the effect as deny if mandatory tags are missing from the request payload. It defines the rule for environment and owner tags, ensuring that any resource creation request without these values is immediately rejected by the Azure Resource Manager engine. This automates governance and prevents configuration drift during rapid scaling phases. Finally, we enforce policy to fully automate compliance across every deployment pipeline. The last step involves using tools like Azure Policy Initiatives or Terraform Sentinel checks to ensure no resource is deployed without required tags or locks. This automation provides developers with a safe sandbox, allowing them to move fast while maintaining stability and financial control, because manual enforcement inevitably leads to overlooked exceptions and budget overruns. Understanding inheritance is absolutely critical for the certification exam scenarios you will encounter. Locks propagate strictly from parent to child resources within the same management hierarchy. If you apply a lock at the subscription level, every resource group and resource within inherits that restriction automatically. This creates a governance gridlock risk if not managed carefully, because overlocking can block necessary updates and halt automated deployment pipelines entirely. Governance should facilitate innovation, not stifle it within your engineering teams. By automating these controls through policy definitions, you provide developers with the freedom to move fast within a safety sandbox. This ensures that their speed does not come at the cost of stability or financial control, striking the perfect balance between agility and security, because manual checks inevitably introduce human error and delay critical production releases. we have covered the essential pillars of cloud governance for your certification journey. Resource locks protect against accidental deletion, while tagging strategies provide the metadata backbone for cost and operations. We implemented these controls by defining schemas, applying locks, and enforcing policy automation across every subscription. Remember to avoid pitfalls like inconsistent tagging and overlocking management resources, which can paralyze your deployment pipelines and trigger unnecessary audit failures. For the AZ-305 exam, focus strictly on the distinction between read-only and cannot delete locks during scenario questions. You will likely encounter scenarios requiring you to choose the correct lock type for a given business requirement involving database maintenance or storage archival. Also, remember that locks are inherited, so applying them at the subscription level affects all child resources instantly. Finally, emphasize policy as code as the gold standard for governance, because manual overrides will definitely fail under time pressure. Imagine you're planning a massive new city without a master blueprint. If every developer builds their own roads, power grids, and zoning laws from scratch, you end up with chaos and infrastructure that cannot scale. In Azure, this happens when teams provision resources without governance. Configuration drift creeps in, security gaps appear, and costs spiral out of control before you notice. Today, we will learn how Azure Blueprints and landing zones act as your official city planners. They provide standardized frameworks that keep your cloud secure, compliant, and ready for enterprise scale from day one. Here is our roadmap for this lesson. We will start by defining the drift problem and explaining why strict governance matters for compliance audits. Next, we will break down the core components of an Azure landing zone architecture using Cloud Adoption Framework guidelines. Then, we will walk through implementing blueprints step by step with real PowerShell commands. Finally, we will cover best practices and common pitfalls to watch for on the AZ-305 exam, so you avoid costly configuration mistakes. Let's start with the Azure Landing Zone. This is not just a resource group. It is a conceptual framework based on the Cloud Adoption Framework that provides a pre-flight environment for your applications. It accounts for scale, security, governance, networking, and identity. The goal is to ensure that every subscription follows your organization's gold standard from the moment it is provisioned. Enterprise environments require this separation to maintain compliance and prevent unauthorized service deployments from breaking your network topology. Visually, a landing zone relies on a hub-and-spoke topology managed through management groups. At the top, you have the Platform Management Group, containing your connectivity subscription for the Hub VNet and your management subscription for log analytics workspaces. Below that, the Landing Zones Management Group holds your corp and online subscriptions where actual workloads live. This hierarchy ensures platform networking is decoupled from application development, preventing a single misconfigured route table from taking down your entire production environment. Now let's look at how we actually implement this using Azure Blueprints. Blueprints provide the automation to deploy the landing zone architecture consistently across multiple tenants. We will walk through this process step by step. First, we define the blueprint itself within a target subscription using the Blueprints module. This initializes the container where we will later inject our governance artifacts before publishing the final version. Here is the PowerShell script to define a blueprint. We start by setting variables for your subscription ID and blueprint name. Then, we use new as blueprint to create the definition object inside your target tenant scope. This command initializes the blueprint container where we will later add our artifacts. The output gives us the blueprint object reference we need for subsequent steps, ensuring you track version control correctly from the start. Once the blueprint exists, the next step is to add artifacts. Artifacts are the building blocks that enforce your standards across every subscription. We can add policy assignments to lock down regions, role assignments for permissions, or ARM templates for infrastructure. This step populates the blueprint with your governance rules, preventing developers from accidentally deploying resources in unsupported locations or bypassing mandatory tagging requirements. In this code snippet, we use AZ Blueprint artifact to attach a policy assignment to our blueprint. We specify the artifact type as policy assignment artifact and point it to the specific policy definition ID for restricted locations. We also pass parameters to enforce tagging, ensuring every resource created under this blueprint carries the required environment tag. This automates compliance enforcement and stops unauthorized services from consuming budget before your finance team notices. Finally, we publish and assign the blueprint to your target scope. Publishing creates a version snapshot of your artifacts with a unique revision number like V10. Assigning it to a subscription applies all the policies, roles, and templates immediately across existing and new resources. This is the moment where your landing zone standards become active, but failing to validate assignments first could lock out legitimate administrators during deployment. Let's compare the different artifact types you can use in a blueprint. Policy assignments enforce rules like regional locks or mandatory tagging requirements. Role assignments grant permissions to specific groups using built-in roles like contributor. ARM templates deploy infrastructure components like VNets and subnets. And resource groups create logical containers for your resources. Understanding these distinctions is key for the exam, as mixing them up will cause deployment failures during provisioning. Remember this principle for your architecture design. Guardrails enable speed while roadblocks kill it. Your governance should not block developers. It should create a safe environment where they can move fast without breaking compliance. Blueprints provide those guardrails automatically by enforcing pre-approved configurations. If you skip this step, teams will bypass security controls, leading to unpatched virtual machines and unexpected monthly bills that exceed your allocated budgets. Quick check for your certification prep. In a standard landing zone architecture, which management group contains the Hub VNet and Log Analytics workspace? Is it the landing zone's MG, the platform MG, or the root MG? Think about where platform-level networking belongs. The correct answer is the platform MG, because placing core infrastructure in workload subscriptions violates separation of duties and increases your blast radius during a network outage. Now let's cover best practices for production environments. First, adopt policy as code using Bicep or Terraform to version control your governance rules. Second, leverage management group hierarchy for inheritance by applying restrictions at the root level so they cascade down to every child's subscription. Third, start small with a minimum viable landing zone and iterate rather than over-engineering on day one, which prevents deployment bottlenecks that stall your development pipeline. Let's define a key term you will definitely see on the exam: management group. A management group is a hierarchical container used to organize Azure subscriptions and apply governance policies like Azure Policy and RBAC at scale. It sits above subscriptions in the hierarchy, allowing you to manage multiple subscriptions as a single unit. Misconfiguring this structure will cause policy inheritance failures that leave your resources completely unprotected against unauthorized access. To recap our core concepts, landing zones provide the architecture for secure, scalable environments using hub-and-spoke topology. Blueprints automate this architecture by defining repeatable sets of artifacts like policies and roles through version control. Always separate platform concerns from workloads, use management groups for inheritance, and treat governance as code to prevent drift. Ignoring these steps will result in fragmented subscriptions that fail security audits and exceed budget thresholds. For the AZ-305 exam, focus heavily on the hierarchy of management groups and how policies inherit downwards through the tree. Know the difference between Blueprint artifacts versus standalone Azure Policy assignments in the portal. Understand that landing zones separate platform subscriptions from workload subscriptions using distinct management scopes. Finally, remember that blueprints are being supplemented by deployment stacks and bicep modules in modern architectures, which will change how you answer scenario questions. Imagine running a restaurant without a cash register or inventory ledger. You might serve delicious meals, but you will never know if you are actually making money or slowly going bankrupt. In the cloud, cost management acts as that financial dashboard. It establishes the guardrails, visibility, and accountability needed to ensure every dollar spent on infrastructure delivers tangible business value rather than leaking into waste. Without proper governance, a misconfigured Azure App Service plan can silently spike your monthly spend, causing unexpected invoices that drain operational budgets. We will cover designing a governance strategy through 3 key pillars: implement budget definitions using infrastructure as code, explore allocation models, and review best practices to avoid common pitfalls. You will learn to deploy cost tracking templates via the Azure CLI as deployment group, create command, ensuring every resource inherits proper metadata from creation. Understanding these frameworks prevents untracked sprawl that quickly inflates monthly invoices, while mastering ISC automation guarantees your financial controls scale alongside your application architecture without manual intervention. First, we establish visibility. You cannot manage cloud spend without comprehensive tagging. Mandatory labeling allows you to categorize resources by department, project, or environment, giving you the granular data required for accurate reporting. We will enforce these tags using Azure Policy definitions that automatically reject deployments missing critical fields like cost center or owner. Failing to implement this step creates blind spots where orphan databases accumulate charges indefinitely, making it impossible to allocate expenses correctly across engineering teams during quarterly audits. This Azure Policy definition enforces a mandatory cost center tag. The policy rule uses a not condition to check if the tag exists. If it is missing, the effect is set to deny, blocking resource creation until compliance is met. You will configure this rule by assigning the built-in policy named Require Cost Center tag and linking it directly to your subscription scope. Skipping this enforcement allows developers to provision untagged virtual machines that bypass financial tracking entirely, which guarantees unexpected budget overruns during peak deployment windows. Next, we define allocation models. You must decide how costs are assigned to teams. Showback provides transparency without direct billing, while chargeback actively debits departments based on consumption to force accountability. We will configure these models using Azure Cost Management, reports filtered by specific resource groups, and linked invoicing accounts. Choosing the wrong model leaves engineering squads unaware of their actual infrastructure footprint, which directly causes redundant service deployments and wastes compute capacity that should have been right-sized during the planning phase. Showback reports usage costs to departments for awareness without actual billing, whereas chargeback directly debits budgets based on resource consumption to enforce financial accountability and optimization. You will implement chargeback logic by integrating Azure Billing APIs with internal finance portals that automatically deduct monthly compute fees from departmental ledgers. Confusing these approaches leads to misaligned incentives where teams treat cloud resources as free utilities, resulting in unoptimized virtual networks and wasted storage tiers that inflate your operational expenditures without delivering measurable business outcomes. Finally, we enforce control. Budgets act as the brakes for your environment. By setting thresholds at specific percentages of a forecasted limit, you can trigger automated notifications or remediation workflows to prevent overspending. We will configure these limits using the As account budget create CLI command with precise amounts and email contacts for immediate escalation. Neglecting this control mechanism allows runaway scaling operations to consume reserved capacity unexpectedly, which triggers hard service quotas that crash production workloads and violate your organization compliance requirements. This ARM template creates a monthly budget resource. It sets the amount to 1,000 and defines a notification that triggers when spending is greater than 90% of the limit, sending an alert to the finance team email address. You will deploy this configuration using As deployment create with a properly structured JSON file that specifies the Microsoft consumption budget's provider and includes webhook endpoints for PagerDuty integration. Failing to automate these definitions causes manual tracking errors where engineers miss critical spending thresholds, leading to unapproved resource provisioning that exceeds your quarterly financial targets. Beyond notifications, you can implement automated remediation logic. When a budget threshold is exceeded, the system triggers a function that stops non-production virtual machines or scales down auto-scaling groups to minimum capacity. You will wire this workflow using Azure Logic apps connected to action groups that execute power-off commands against development subscriptions during off-hours. Skipping this automation leaves idle compute resources running continuously, which rapidly consumes your allocated monthly spend and forces engineering teams to manually intervene before production workloads experience resource contention. Common pitfalls include setting budgets and forgetting to adjust them as the business scales, which renders the budget irrelevant. Lack of granularity makes data ineffective for action, while ignoring data transfer costs creates hidden egress drains that quickly consume your forecast. You will mitigate these risks by configuring quarterly review cadences in Azure Cost Management and enabling detailed breakdown reports for virtual network peering traffic. Failing to update these parameters causes false positive alerts that desensitize stakeholders, ultimately allowing unmonitored storage replication fees to silently breach your financial boundaries during peak data migration cycles. Familiarize yourself with the FinOps Foundation framework. It represents an evolving cloud financial management discipline that enables organizations to get maximum business value by helping engineering, finance, and business teams collaborate on data-driven spending decisions. You will apply these principles by implementing continuous cost optimization cycles that track right-sizing recommendations for Azure Kubernetes service clusters and monitor reserved instance coverage across mixed workloads. Ignoring this structured approach results in fragmented financial ownership, where developers deploy expensive premium tiers without approval, directly undermining your overall cloud ROI targets. What is the primary purpose of setting budget thresholds at multiple levels like 50, 80, and 100%? It allows you to trigger automated notifications or remediation workflows before overspending occurs, giving teams time to react. You will configure these progressive alerts using Azure Cost Management budgets that send distinct email notifications to project leads and subscription administrators at each defined percentage mark. Skipping this graduated approach forces engineers to discover critical spending breaches only after service limits are reached, which triggers immediate resource throttling and disrupts active application deployments across your environment. We covered visibility through mandatory tagging, allocation models like showback and chargeback, and control via budgets and automation. Remember that cost governance is a continuous process requiring regular reviews and actionable alerts. You will solidify these concepts by implementing Azure Policy initiatives that enforce resource naming conventions and linking them directly to automated budget tracking dashboards. Treating financial oversight as a one-time configuration instead of an ongoing practice guarantees untracked resource sprawl, which steadily inflates your monthly operational expenses and compromises your ability to forecast accurate infrastructure requirements for upcoming release cycles. For the AZ-305 exam, focus on designing governance strategies that align with business goals. You will need to configure budgets and alerts effectively, understand the difference between showback and chargeback, and implement policies to enforce tagging for cost allocation. You will encounter scenario-based questions requiring you to select appropriate Azure cost management features and evaluate policy definitions that restrict unauthorized service deployments. Failing to master these architectural controls results in incorrect answer selections where you overlook critical compliance requirements, ultimately preventing you from demonstrating the required cloud financial governance expertise on the certification assessment. Imagine a library where anyone can grab any book and leave it on the floor. Chaos, right? Cloud governance acts as that strict cataloging system, keeping your digital environment secure and efficient. For the AZ-305 exam, you must understand how built-in policies enforce tagging on every resource group. Without these automated guardrails, developers spin up untracked virtual networks, causing massive billing surprises and compliance failures during audits. We will explore the 5 core cloud adoption framework disciplines, dive into policy as code with real examples, walk through a complete implementation workflow, and review best practices to avoid common pitfalls. You will learn to configure Azure Policy definitions using JSON parameters like allowed locations and assign them via AZ Policy Assignment Create. Mastering this sequence prevents orphaned resources from drifting outside your compliance boundaries during active deployments. The Microsoft Cloud Adoption Framework structures enterprise governance into 5 distinct disciplines covering strategy, platform, security, operations, and management. Each discipline translates abstract business requirements into enforceable technical controls. When you configure subscription-level policies with specific numeric limits like allowed resource types, you automatically prevent unauthorized service deployments. This structured approach eliminates manual review bottlenecks while guaranteeing consistent security baselines across every workload. Policy as code represents the practice of codifying governance rules directly into machine-readable templates instead of relying on retrospective manual audits. This methodology automatically enforces compliance at the exact moment a deployment request reaches the control plane. By defining strict JSON schemas that block non-compliant parameter values, you prevent unencrypted storage accounts from ever materializing. This proactive stance eliminates costly remediation cycles and keeps your architecture audit-ready. Here is a practical Azure policy definition that strictly enforces mandatory tagging. The rule evaluates whether the environment tag property exists within the request payload. If the field remains empty, it immediately applies a deny effect to block the operation entirely. This mechanism prevents non-compliant virtual machines from ever provisioning in your subscription. Failing to implement this check leads to untagged assets that complicate cost allocation and breach regulatory requirements. Let us walk through implementing enterprise governance using a structured 3-phase approach. First, we author custom policy definitions that establish your baseline security rules and operational standards. You will construct these definitions using the Azure Policy Portal or PowerShell scripts to specify exact parameter constraints. Establishing precise definitions upfront prevents ambiguous enforcement rules from confusing development teams during rapid deployment cycles. In this initial step, you create the actual policy definition object within your management group hierarchy. The JSON payload defines the evaluation logic by checking for specific metadata fields and applying an effect like deny or audit if not exists. You can reuse these exact definitions across multiple subscription assignments without rewriting code. Skipping proper parameter validation causes conflicting enforcement rules that silently allow prohibited resource types to deploy successfully. Next, we assign these compiled policies directly to a defined administrative scope. This critical linking step connects your abstract rules to specific management groups, root subscriptions, or individual resource groups so they immediately take effect. You must carefully map policy assignments to match your actual organizational hierarchy rather than scattering them randomly. Misaligned scoping causes conflicting enforcement overlaps that trigger unexpected deployment failures across unrelated engineering teams. Use the Azure CLI to formally assign the policy directly to a target subscription. The command specifies the exact policy definition, ID, alongside the target scope parameter to establish the enforcement boundary. This precise targeting ensures the governance rule applies uniformly to all resources created within that specific account boundary. Forgetting to explicitly define the management group hierarchy allows developers to bypass restrictions entirely using alternative deployment paths. Finally, we continuously monitor compliance status and actively iterate on the policy definitions. You must track configuration drift using automated assessment reports and refine enforcement parameters as your cloud footprint expands. Regularly reviewing non-compliant resource counts prevents security gaps from accumulating unnoticed across your environment. Neglecting this iterative maintenance phase causes outdated restrictions to become completely irrelevant, while critical vulnerabilities remain permanently unaddressed. Monitoring involves checking compliance status regularly through dedicated dashboards or automated log analytics queries. You will identify non-compliant resources by filtering assessment results against specific policy assignment IDs and subscription names. This continuous feedback loop allows you to adjust enforcement parameters and fix configuration drift before it negatively impacts daily operations. Skipping regular compliance reviews causes unmonitored deviations to accumulate, eventually triggering severe audit failures during external assessments. Avoid common pitfalls like governance bottlenecks and completely static policy configurations. Instead of relying on tedious manual approval workflows, implement automated guardrails that enforce compliance silently in the background. Provide structured exception pathways for legitimate shadow IT initiatives while maintaining core security baselines. Reviewing your enforcement posture quarterly prevents rigid rules from blocking essential business innovation and ensures continuous alignment with evolving regulatory standards. Always remember the fundamental principle of least privilege when designing access controls. Give users and automated service principals only the minimum permissions required to perform their specific tasks, absolutely no more and no less. You can enforce this concept by assigning built-in roles like reader instead of contributor across development subscriptions. Violating this principle creates excessive privilege accumulation that dramatically increases your attack surface during credential compromise events. Quick check question for your certification preparation. Which specific Azure policy effect completely prevents resource creation when validation fails? Carefully consider the operational difference between a soft audit alert and a hard deny action. Applying the correct enforcement type stops unauthorized virtual networks from deploying immediately rather than merely logging a warning. Confusing these distinct effects causes exam candidates to misconfigure deployment restrictions and miss critical security controls. We covered the 5 core governance disciplines, explicitly defined policy as code mechanics, walked through complete implementation steps, and reviewed proven best practices for enterprise environments. Governance acts as a critical enabler that balances rapid development velocity with strict operational control. Mastering these concepts ensures you can deploy compliant infrastructure efficiently while preventing costly misconfigurations from disrupting production workloads. This balanced approach directly aligns with certification exam objectives. For the AZ-305 exam, focus heavily on distinguishing specific policy effects and understanding core governance disciplines. You must know how to assign policies directly to management group scopes and recognize best practices for avoiding manual bottlenecks during deployments. Practice configuring JSON parameters for allowed locations and allowed resource types before test day. Mastering these technical details prevents careless mistakes that frequently lower certification scores among unprepared candidates.